Uh, Thank you, everybody. Hello. Welcome to that text, which is TechNet Earth Global Symposia. This is the eighth episode of the history of physics, and I am with Christopher also, who has come. We both are there for all of the thing, and we hope that others may join, when Song or Manuel, whoever is able to do. But you can always watch these videos. We have run the history of physics quite successfully, and that there are enough viewership, but we are not gone public in the sense of telling the whole world about it. But eventually we might. We plan to complete this episode up to 10 by February, so we are the ninth one, which may talk about the contemporary history, because we are moving into that, and or transitioning to that. And then the 10th will contemporary physics with emergent. So we'll just glue together that the current things that's going on, emergent technology of granified physics. So I think it is all coming together well, and hopefully we'll have a documentary movie and all this to make the general public to understand that in a very simple manner, like Oppenheimer movie. So the episodes until now talked about started with a very simple understanding of Newtonian and Galilean, and still I think that's probably the best, because they are very measurable scalar quantities. And later on, because of the ultraviolet spectroscopy and Viking spectroscopy, you have the incorporation of the quantum theory with the Planck, found a way to resolve the problem with the classical physics. And then Einstein came along and then started the relativity theory, uh, to find the constancy of speed of light, and max, especially uh, motivated by Maxwell equations and the field theory, and then way to unify all the theories. And as we know that many of the atomic theory, and this is the previous episode, like episode 4 or 5, we talked about the Maxwell equation, but really the Rutherford and understanding of the particle physics, uh, eventually became the particle physics, the atomic theory, came after Maxwell. So the Maxwell has kind of looked into it and kind of predicted these, but experimentally this was shown, and that kind of changed the whole realm of physics and went into the understanding of quantum physics. Because again, Bohr came and then said, in one episodes we described that, uh, episode 3, 4, and 5, I think, concentrate on this, how the quantum theory came into being. And it was a necessity, but also it was a problematic aspect, because the math became more complex, the operator algebra, things like that. So essentially, talked about the relativity theory, talked about Lagrangian of energy to describe the equation of motion. Very much similar in Newtonian and uh, Galilean that we use every day. Speed, distance, time, these are very simple variables. And the classical thermodynamics, which one of the episodes concentrated on, talks about very simple thing like time, temperature, transformation that we use every day. Temperature we measure. So these aspects still are very important, but the Lagrangian and the Hamiltonian took over. And in the part of physics now, the concept of time is very only implicit. The wave function aspects start coming, and then I'm looking into that more, and Christopher is looking into the space aspect, because the Einstein theory, then because he understanding of space and time as a complete unit together as a four-dimensional entity is still an ongoing debate. Uh, so these are all ongoing things, but we are advanced to the level that each episode, once we see uh, in episode 1 to 7, you get an understanding without too much of complex math, of how they progressed through time. So this is what like to continue. And the eighth episode talks about the gravity, space, time, quantum locality, astrophysics. So they are all different elements. You see that try to unify them, and now everything is understood in terms of quantum gravity. That in the sense that the astrophysical level larger is still the gravity is what is holding everything together without everything flying apart. Although Hubble thing, it's expanding in that from the Hubble theory, but that's again, all of them are brought to question under different observations, and the recent observation with the James Webb telescope and or requires modification of these things. But uh, the quantum gravity essentially tries to see how we can patch up with the quantum mechanics with the relativity aspect. So the gravity is a local phenomena. That's what's coming up, and the swampland conjectures, things like that, which I think I touched upon in the seventh episode, and this episode also probably briefly touch upon, is that it tries to bring together string theory. And as you have mentioned, the previous fifth or sixth episode, the string theory became the most beautiful mathematical explanation of the whole physics. But there are problems. When you incorporate a standard model, they seem to be okay, but when you talk about gravity, they fall apart. So there are like five different string theories. They had to be brought together in something called the M theory. That's one of the things that I'll be talking about. So, uh, like I said, these are all available, in the YouTube uh, version of it, and then we have a way to look into all of the videos that we have recorded on this site, TechNet Global YouTube site, and then eventually we want to have uh, like I mentioned before, a conference, world conference, and then we'll talk about the Holy Grail and start with that, and then we'll have a separate room where we start presenting, and this could be one of the things that could unify all that and bring together, uh, on the same page for everybody to understand that. So we continue with the historical perspective with non-locality approach. So this is very important because what happens in quantum mechanics, the question of locality versus non-locality became a debatable point. So in 1964 to 1990, John Bell was one of the key persons, and he still is. The Bell's theorem is one of the top level quantum understanding, and now in the quantum computing world, this is becoming very important. These theories. So the notion of non-locality underwent significant changes. Evolution of non-locality theory. So what he said was the local hidden variable, which Einstein has pointed out, problem with the quantum mechanics, can't explain entangled states that may happen or occur between separate particles. So that a quantum entanglement, superposition, things like that became very important part, and the multiverse theory. Uh, I mean the multiple presentation of the wave function that comes out of quantum mechanics. All these says that uh, the local hidden variable cannot explain that. So challenge the classical notion of locality, which states that distant events cannot instantly influence each other. So classical physics, that uh, essence of locality is there, that whatever happens locally uh, will not affect the global aspect, essentially. So gradual detachment quantum mechanics. Over time, Bell's non-locality theorem became detached quantum mechanics, referring to the wider probabilistic theory involving correlation between separated variables or observable quantities. Uh, so the quantum mechanics again is highly localized in that sense that the wave functions are originated locally with the particles, things like that. But Bell's non-locality theorem, essentially was trying to falsify that observable quantities, things like that. So proposition of standard quantum mechanics violating local causality became distinct to Bell's theorem. So that local causality, so to say, sorry, or local realism, the causality aspect is not really local according to Bell's theorem. That's what he was trying to prove. So local causality and special relativity. So Bell introduced the concept of local causality in 1976, absence of superluminal signaling in physical theory. So, uh, so there is no, according to Bell, which he originated from special theory, which says that you cannot have anything faster than speed of light. So that's the limit that Einstein theory, the relativity theory says, especially the special relativity. And so there is no superluminal signaling. There is no instantaneity in that sense. So how do you reconcile to that? This was the problem that Bell took up. So Bell expressed concern about non-signaling theorem in quantum mechanics, touching on the anthropocentric elements in the orthodox quantum thinking. So essentially the people, how the people are involved, and you will see that, and we have mentioned briefly, and I'm not going to details of the math and details of the logic. But essentially, we talk about Alice and Bob and all that, how they go. But not only in black holes, uh, event horizon, things like that, how they will communicate, but also that is extended to the quantum mechanics. So the people involvement are important, and there are a lot of experiments conducted with people in different places, and then how they communicate with each other, things like that. But the idea of non-signaling theorem was one of the key aspects. But that Bill took upon that there could be a shift. So the belt shift in thinking occurred. Uh, the factorizability condition. Excuse me. So no correlation was not seen as a formulation of local causality, but a consequence only. So the local causality is a consequence of that, but it is not a fundamental aspect. So, what exactly? How an issue of strict inconsistency between violation of factorizability and special relativity is unresolved by whose thinking shifted paradigm. So, there is a problem of violation of the Bell's theorem. Okay, that we'll come across that many times. Um, the question of factorizability. So this was one of the key things, Bell, and it's not very clear yet how that came about, and we have to look into more, and we'll be looking into more aspects uh, because it comes to the quantum computing, the real world, that we may have to spend a little more time on understanding that. There's no clear understanding of how these came about, but there are many other people who came about, like Everett interpretation and Lorentz covariance. So Bell's theorem, understood by considering Lorentz covariant version of quantum theory. So the Lorentz theorem, the variation uh, by the transformation, Lorentzian form, is important because to connect with the relativity, we need that, the special relativity, essentially a Lorentzian transformation aspect. So if we can connect somehow, people thought that we may be able to resolve the problem between quantum mechanics and relativity. So these things started becoming important, the mathematical manipulations. So the Everett interpretation of many words interpretation, like I mentioned before, the quantum mechanics is is extended to consider the fact that the wave functions are everywhere. And I could briefly, understand that in terms of the vector aspect. The wave function is a vector. So the vector space, the vector doesn't stay in one place. It's not fixed in one place. You can have a vector here, another vector some other place, and they are easily transmutable. You know, so the vectors don't can move around freely in space. Only the scalar aspect is fixed with respect to a coordinate system, and this is going to bring out this in by one of the papers in reference system. reference frames. So the vector aspect, I can have vector anywhere and move it around, and they don't have any particular location. So one vector, I can resolve the vector and move the vector, and then if there are two vectors here, I can move them around in space. So the vectors are easily mobile in that sense. They have no fixed space in that sense. So that's how very close to many worlds interpretation came into being. And this is a Lorentz covariance aspect uh, aspect that came into being uh, without action as a distance. So that is the action as a distance is that you can actually move that. It is not fixed in one place. The action is, so it's not really local in that sense. So they're moving away. The vector actually helps to understand the vector in vector space or Hilbert space. You can actually move these around, and there is no particular locality in that sense. So they're trying to bring out together, but there is a problem of the math, consistency there, and that's what's going on presently. The experimental test to prove the Bell inequality was done by Alain's aspect, and as you know, he's also a Nobel laureate in that sense. Uh, these are all, many of them are Nobel laureates because specific things they did. Ensuring measurement settings were independent of the source. Aspect showed entangled photons, variable settings of polarizers, giving evidence against local hidden. So, Alain Specht, by using entangled photons, and these are ongoing experiments. The Chinese, there is an experiment. Chinese, they were able to entangle photons were even separated in space, long distance, and I think in satellite by satellites, things like that. And that's going on now. So the photons in one place communicate with the photon in a far distant place. It could be light years away. And this entangled photons aspect showed by experiments on Earth, how these you can use polarizers to create entangled photons, and that entangled photons communicate. So there is no, so he proved that there is no real hidden variable or the localization of the aspect. Essentially, he was proving the non-locality aspect. So, so classical physics and locality. So going back to classical physics, the locality states that an object is directly influenced only by its immediate surroundings. This was the idea of, uh, the main concept behind Newtonian and Galilean aspect. The local surroundings is what's disturbing. The principle aligns with the idea that interactions such as gravitational and electromagnetic forces propagate through space at finite speeds, adhering to the constraints of special relativity. So they essentially are produced locally and then they propagate. So like wave propagation, the waves are produced locally and then they propagate. So there is a separate aspect of initiation and then propagation aspect. So these are separate events. The quantum field theory and locality. So these incorporates principle of locality at the field level. Both quantum mechanics, special relativity working together. In QFT, in the quantum field theory, interaction mediated by fields that propagate finite speeds. So the additional aspect in the quantum field theory, as we did that earlier, is that there is a mediator. There is a mediator, and this mediator is the fields that propagate finite speeds, like conforming to the spectral relativity of speed of light. So, for example, Feynman formulation, things like that. Causality is preserved there. So the Feynman diagram does show the how like a positive electron mediated by photon can produce the quarks and things like that, and also uh, you know even gluons and all that. So that's the whole aspect of quantum field theory, which forms the basis for standard model as well. Quantum gravity and locality. So when you talk about the gravity, that's a complex issue, as we have mentioned, and still is. The cost for a theory of quantum theory raises question about nature of locality at Planck scale. So now The idea that everything, all the particles has a finite dimension, in the sense of the smallest dimension you can have is a Planck scale dimension. So the loop quantum gravity and string theory explore the possibility of space-time being fundamentally discrete. So, so essentially, what it means that, like I worked with Emery, there is a discreteness of space. The space is not a continuum in that sense, the classical sense. So the loop current gravity and string theory states that the space-time actually is discrete, modifying understand locality. So if it is discrete, how it can be local? You know, the local aspect. How do you reconcile to the aspect of discreteness? That's always a problem. So the locality is called into question. Holographic principle and uh, add CFT, which is Andy de Sitter and all that, and then conformal field theory, correspondence. So all of them have a lot of abbreviations because they club together, a lot of the aspects together of the people, and the abbreviated aspect could be sometimes confusing, but we are trying to resolve that, and then expand as much as possible to explain what they are. So Hooft, who was another Robert Oryat, very important person, and Susskind in Stanford University professor of physics, quantum and related physics, proposed a holographic principle. So holography has been experimentally proved, although it has not developed recently. But initially, they said that, for example, uh, one of the earlier presidential candidate in U.S., Gore, uh, was actually holographically present in another place. So yeah, you can have a person here, and the holographically it can be projected somewhere else, as if that person is really there. So that's a very nice application of this, and prove some aspects of the holographic. The information contained by volume of space can be represented as a theory on the boundary of space. So it's a very important developing theory. And it also came from the idea of black holes, that the black holes initially they thought that they will destroy all the information, but that's not true. The information goes on on the boundary of that space, and then Penrose, other people have expanded on that and developed theories. Physics via data on the boundary. So the data stays on the boundary, so we can access the data. Uh, you know, Originally maybe in the volumetric aspect, the volume aspect, but then the surface aspect. Go if you think of a simple aspect, a sphere, the information is contained inside the sphere volumetrically, but that information is spread out on the surface of the sphere, for example. So it's available from there. So tapping the surface of the sphere, we can actually get information. That's one of the aspects of the non-locality. And then that comes in the idea of ASTROPHYSICS, which is anti-de Sitter space. As you know, the de Sitter space and anti-de Sitter is a difference in how we look at it. If you are inside a box or inside that sphere, we have the de Sitter, and then we go outside of that and look into that, the surface, that's anti-de Sitter. So one of the persons who won Maltasena had posited duality between gravitational theory and anti-de Sitter space. So we are looking at gravity from outside and how they interact. That's anti and the conformal field theory on the boundary. So the boundary aspect is between that conformal field theory. So these require a little more explanation and discussion. We'll be going to that later on. But let me proceed to the continue with that, because that itself will take a long time to describe. So essentially, we are going to the historical path, so we will move on. The duality means that a higher dimensional gravitational theory can be fully described by a lower dimensional non-gravitational theory. So that's the idea of, when you go up, we have the dimensions changing. Again, that's a complex issue. But we have lower dimensional non-gravitational theory suggesting space, time, and gravity emergent phenomena of the boundary theory. So in the boundary, you have both coming together. That's the idea. And the conformal field theory tries to merge together these two ideas. So if you have quantum mechanics, say, operating inside, and you have the relativity operating outside, then we can bring together in the boundary, in the conformal, both of them together. That's one of the simple idea. So, or of geometry, a lot of geometry is involved. Geometry. The geometry is a very important part of physics. So we have to consider seriously uh, that aspect, because that's going to help us to unify things. So space-time structure per quantum gravity. A Planck scale, which is discrete per loop grand gravity, continuous per string theory. Classical space-time emergence is transitioning from quantum to classical space-time is crucial. So the classical aspect, why we consider always, is because the measurements is automatically facilitated by the classical physics. So we have to reduce everything classical physics, because the actual scalar quantities, which are measurable things, are classical. Uh, but when you quantum mechanics, or if you go to relativity, there are vector and tensor, which are not really measurable. So I emphasize that later on in reference theory, the vector quantities require a proper reference frame to be measurable and become classical quantity. So that, as we always have to consider that. So observable phenomena, then, when you talk about speed, light specifically, 3 times 10 to the power 8 meters per second, that's, you are scalarized, it's a classical quantity. So we have to come down from the quantum mechanics, or relativity theory, into that classical measurements. So loop quantum gravity supposes coupling of matter fields to gravity. So this coupling aspect is another aspect that is upcoming. Uh, so the fields exist as vector quantities in vector space, and the gravity. So the matter has its own field, and then, let's say mass vector, whatever, and that, how that couples to gravity is one of the key things. And I do describe that about the gravity being not a fundamental thing, but it's a gradient, but then it couples to the matter field. So that's an interesting aspect that's developed. But important things that really was proved by experimental methods, that goes along the idea of grinding theory, or also quantum field theory and advancement of that, the uh, Young Mills model, things like that. How they come together is the altropic unification of particle medium bosons. So the altropic unification is a fundamental aspect of particle physics that describes unification of electromagnetic and weak nuclei. So the first one, unification aspect, that Einstein wanted, it was his dream of unifying all the fields, all the four fields, as we know, the super fields. You have the gravitational, the electromagnetic, the strong nuclear, and the weak nuclear. That was very difficult to do. But the in 1960s, Sheldon Glashow, Abdas Salam, and Steven Berger were given Nobel Prize for their work on the altropic unification, which essentially means that they unify the electromagnetic and the weak nuclear forces. And the key concepts are gauge bosons. Uh, so the mediation aspect, which was in the quantum field theory, Feynman diagram, things like that, essentially was extended by these scientists. Uh, Exchange of gauge bosons. So the understanding of gauge bosons is very important. So electromagnetic interactions is the mediator. The gauge essentially removes a lot of redundancies. We can think of gauge as a way to unify things by removing trivial things or redundant things. So, so gauge bosons essentially can act as a mediator. The mediators are identified as W and Z bosons. So again, this whole theory that was developed, W plus, W minus, and Z zero, and they have specific properties. I'm not going to go into details of that. That itself is a discussion by itself. But the understanding is that spontaneous symmetry breaking, the Higgs mechanism. So the person who was successful in doing that was Peter Higgs, who got Nobel Prize also recently. and it was proved by the LHC, the Large Hadron Collider experiments, which showed the signals, the spectroscopic signals that Higgs has predicted. So, and that's called the God particle, because they give the mass, the Higgs boson, gives mass to W and Z bosons, leaving the photon massless. So again, that question again is a big thing. Is the photon really massless? It's just a pure wave, or does it have mass? We don't know yet. But essentially, uh, W and C bosons have mass, and they generally facilitate spontaneous symmetry breaking. So, which means that it will go in the side of the matter, the real matter universe. That's the crux of the things right now. How these asymmetry occurred between matter and non-matter. So, in that context, Weinberg angle became one of the key aspects. The mixing of the electromagnetic and weak interaction characterized by Weinberg angle, or the weak mixing angle. It means the relative strength of the force. So essentially, the angle talks about the strengths of the electromagnetic force versus the weak interaction, the weak nuclear forces. So there's a specific angle at which they merge together, they mix together. The Higgs boson is a crucial part of electroweak theory. In 2012 at CERN, uh, it confirmed the Higgs mechanism that gives mass to the W and C bosons. So again, that became the strength of the standard model, uh, essentially. So application implications. The particle interaction. Electroweak theory explains various particle interactions, including beta decay, which was originally started from Rutherford experiments, which is a type of weak radioactive. So radioactivity, as we know, that was earlier Curie and other people have studied, and they got more than one Nobel Prize for that. And this radioactive decay was important, which was the basis for uh, the black body radiation, things like that. So an unstable atomic nucleus transforms a more stable one. This is the idea of a beta decay. So a beta minus becomes a neutron, uh, and then they decay into proton, electron, and muon and things like that. So the proton again decays into neutron, electron, and the muon, the part of the other aspects of electrons. There are more aspects, massive electrons versus non-massive. So they all come into picture here in this aspect. So there are muons and tau electrons, things like that. The electron capture occurs with so you can have a reverse process where protons and electrons combine and they produce neutrons and produce the muon. So this may be what's going on in the deep, you know, nucleus. The nucleus aspect is created where this is going on. So how they patch together, we'll see. So this standard model describes the fundamental particle interactions. It's based on the electroweak theory that essentially sealed the aspect of the standard model, and it was experimentally verifiable from that standpoint. And this is tested and verified through experiments and CERN and Fermilab uh, locations to a very high degree of accuracy. You know, so that was what sealed the deal in that sense. So then the unification aspect became strong. So the unification of strong electromagnetic and weak forces, or the GAN unification theory, what we call GUTs or GUTs, try to unify strong nuclear with the weak, ultra weak force into a single force. So that was the next step. While ultraweak unification occurs, energies around 100 GeV, uh, guts proposed unification much higher energy. So the energy levels are very different, and that's the difficulty with LHC. You have a limit up to half the energy levels you can go to observe them. So for higher energy, we are talking about 10 to the power 16 GeV, which is too high now, not achievable now. So guts predict further existence of new particle interactions that are not part of the standard model. At that level, you have all new exotic particles coming into picture. They have very high masses. They were supposed to have high masses. Whether that will prove about the dark matter things, we don't know. The winds and things like that. Making it difficult to detect the current technology. Both theories relate to concept of gauge symmetry, spontaneous symmetry breaking. So again, the gauge symmetry is another aspect. So you see that how they all get entangled and becomes very very complex math and physics. So we are trying, and that's one aspect that we see is very hard to separate them into a simpler aspect of physics that classical physics was able to see. So people are going back and see how we can glue together all that. And in that midst of things, the quantum chromodynamics, the strong theory, to bring together strong theory into the electroweak theory, the quantum chromodynamics came to be. So the fundamental particles are quarks and gluons, and they are the crux of the nucleus. How they are hold together confinement, how they are able to uh, hold together, although they have opposite charges. So how they are bringing to the protons together and things like that, and the electrons together. Quarks are the building blocks of. So everything is described in terms of quarks, building blocks of protons, neutrons, and other hadrons. They are called hadrons. That's why hadron collider is essentially a proton-proton collision. Uh, gluons are the force carriers. So we know from Feynman that we are a mediator, but in this case, the mediator itself takes part. They are not. Uh, they are not inert in that sense. So gluons are force carriers that mediate strong interaction between quarks. They participate, but they are also part of that. So the idea color charge come into picture. The quarks possess a property called color charge. There are three types: red, green, and blue. So gluons carry a combination of color and anti-color charges. So we know the gluons are not; they are active. They also transmute, and all that. So the color aspect come into picture. Gauge theory QCD is a non-abelian gauge theory. Essentially means that we can have reversible aspects, commutation aspects, uh, symmetry group SU3. So the idea of non-abelian then will say, okay, this you can have asymmetry, hence how the matter can be produced, and hence how that symmetry breaking can easily occur. So this means the interaction between quarks and gluons are described by mathematical framework gauge theory. So the gauge theory became the central uh, mathematical way to uh, to sort out these aspects. The strong nuclear force, so binding quarks. The strong force is responsible for binding quarks together to form protons, neutrons, and other hadrons. The force is incredibly strong at short distances, but diminishes rapidly beyond the scale. This is a very important property of the strong force. We only see at the very local level. Again, the question of locality, no locality, you see that comes into picture there. But a strong force is a very short range force. So residual strong force. While QCD describes fundamental interaction between quarks and gluons, the residual strong force is what holds the protons and neutrons together in the nucleus. Like I said, the confinement. This force is a residual effect of strong interaction between quarks, that the quark gluon or plasma confinement is one of central issues. So the key concept is the confinement. Quarks are never found in isolation due to a phenomenon called confinement. They are bound together in groups such as proton neutrons by the strong force. So this is the gluing aspect. Asymptotic freedom. At very high energies, short distances, quarks and gluons interact weakly. Property known as asymptotic freedom, which means quarks behave almost like free particles at extremely high energies. So they can be detached from this confinement at high energies, and you get asymptotic freedom, like very similar to ionization in liquids. When you high feeds, you can ionize material like hydrogen and OH, the hydroxyl can ionize and they separate. And the same thing with plasma. Plasma is essentially ionic formation. Essentially, they exist uh, in a, uh, free particles in a plasma, like in stars and other things. So they are free to interact. They are free to go around and produce, electrons and protons separately, and they even become positrons eventually, and then and they combine together photons. So these are all the complex mechanism that's going on. So application and implications. Particle physics. QCD is a fundamental part of the standard model, explaining the behavior of quarks and gluons. So the standard model tries to put together everything. It's like a goulash kind of thing. But it's very similar to a periodic table. That's the idea. Periodic table of the particles. So that's its success, that it can see one picture, uh, even one page, what that is going on. Nuclear physics. Understanding strong force is crucial for explaining stability and structure of atomic nucleus. So you have to figure out all these are going on, but how are they able to hold together these high, high energy forces? High energy experiments, particle accelerators, such as those at CERN, provide evidence for QCD, help explore the properties. So this is our ongoing experiments, high energy. Now they are able to achieve higher and higher energies. Hopefully, some of them may be proved eventually. So emergent physics with the source in gravity loop. Emergent gravity suggests gravity is not a fundamental force, but rather an emergent phenomena arising deeper underlying process. So Eric Welden's theory, this is very recent, uh, in this after 2000. Physicists propose that gravity may be an emergent phenomena analogous to high temperature emerges from microscopic behavior particles. So as we know, we can describe we can talk about ensembles, uh, and from the ensemble theory, like I studied the higher thermodynamics that I studied, we can describe from the ensembles how the temperature come into being. So the gravity is similar, I think so, and there are more and more emphasis on the thermodynamics aspects these days to get more unification. So gravity arises from entropic forces associate changes in information content of speech. So the entropy is the bottom aspect, uh, the logarithm effect, so to say. Uh, we can conduct AS equal to K ln T, things like that. There's fundamental equations that people think are the most fundamental aspects. Then thermodynamic approach. Any properties of black holes can be described using. So now there's Hawking radiation, things like that, uh, which are fully derived from thermodynamics. So this suggests gravity might emerge from statistical behavior microscopically. So this is statistical mechanics which talks about that, and from there, if you have random processes going on, they're statistical in nature, and they become stochastical when it becomes real, because time aspect come into being. Uh, so the space and time come together in some ways. So the source sink dynamics per fluid mechanics. So the understanding that the fluid mechanics can describe them is the idea of eventually superfluid, things like that. Sources and sinks refer to points where quantities like mass or energy are added or removed from the system. So locally, we see, for example, we see in the sea these things happening all the time. The source and sink. Uh, so the locally, you have the vortices coming and they create these extra energies that produce evaporation. So the idea of condensates also come into the picture here. Within emergent gravity, these concepts may be used to know how information or energy flows through space-time fabric. So the energy is transmitted somehow. Uh, these information aspects. So information theory has become very important. So information flow in space-time creates effective gravitational forces. So somehow this information, when you get in the local areas, they create these gravitational forces. Uh, Information modeling and concentration dispersions to be sources and sinks. So some kind of a source and sink mechanism will help to understand the gravity a little more. So loop quantum gravity. So quantization of spacetime as discrete structure, smallest scale, such as gravity and spacetime geometry emerges from quantum states of the gravitational field as emergent property. So the quantum states, eventually create a geometry such a way that quantization occurs, the localization as discrete structure. So they are discrete in that sense. Uh, So this fine structure, we have to go into a deep microscope like LHC, high energy levels, and the idea is that we might see this discrete structure. Connections and implication, unified framework, a combination of ideas from emergent gravity and loop quantum gravity could provide a comprehensive understanding of how space and gravity arise from quantum phenomena. Again, that's a challenging aspect. The experimental challenges are there. Uh, Testing the theory is challenging due to extremely high energies or small scales in nodes. We are very close to the Planck scale to describe the discrete structures. So we are to a very high energy, and it's very hard to resolve that small scale uh, still. So how microscopically we go into the LHC or the CERN experiments. Presently, theoretical physics and high energy experiments explore the ongoing concepts. So the gauge theory is modifying the classical theory. Okay, gauge theory. So what is gauge theory again? Gauge invariance means that physical laws remain unchanged under fields changes in the fields, the local transformations. So that's a very important thing. So we have we look at different rotations, for example, different translations. But gauge invariance, tells that how the fields can remain uh, invariant. The invariance leads to introduction of gauge fields that mediate interaction. So the gauge fields are the mediating, and they should not be, they have to be invariant, but they should not change themselves. Very similar to our idea of moderator and things like that in uh, uh, or catalysis in chemistry, like hydrogen catalyzes by platinum catalyzes hydrogen, but it doesn't itself undergo any change. So that invariance is kind of a different version in physics of the chemistry aspect. Okay, gauge fields. Uh, with classical electromagnetism, gauge field linked to electromagnetic potential mediating interaction between charged particles. So the interaction is brought about by the gauge field. In more complex gauge theories, such as those describing strong and weak nuclear, the gauge fields are more intricate. So essentially, when you have gluons and things like that, how do you describe it? Gluons themselves undergo change. So is gluon part of quark or quark part of gluons? These are very complex things to resolve. At present. Modifying the classical fields, classical electromagnetism. The concept of gauge invariance first applied to classical. By using gauge theory, you can talk about the Maxwell equation. You can rewrite Maxwell equation, the gauge fields. The electromagnetic field, quantified by a vector potential, allows gauge transformation of same physical field potentials. So this is the idea of gauge. Gauge essentially is a differential form. So when you have something constant, suppose I have a field per se constant, when I differentiate, I can remove that constant aspect. Only the variable I can take into account. That's kind of a very simple way to look at the gauge aspect. Yang-Mills theory. Okay, that became the crux. Extending idea gauge invariance to non-abelian groups where order of operations matters. Okay, so you have commutation, not non-commutative aspect there. Leads to Yang-Mills theory. So the theory forms basis of standard model of particle physics describing strong and micro. So Yang-Mills theory essentially tries to put together electroweak and the strong, try to unify them. So they Yang-Mills became application and implication. Electroweak unification. Unification of electromagnetic and weak force into electroweak theory, like I mentioned before, Planck is example of gauge theory. Again, in terms of the gauge theory, uh, that unification was a success in that sense. Gauge fields in the theory are W and Z bosons and photon participating in the mediation aspect. The quantum chromodynamics theory of the strong interaction. It's a non-abelian gauge theory of. Now we talked about gauge groups now in terms of space, geometry. We have the group theory, and that is as a special unitary group mentioned in one of the earlier episodes as SU3. Uh, Gauge fields in QCD are gluons. So you have the SU2, SU2, SU3, and the U1 and all are coming into picture here. The gauge fields are gluons which mediate interaction between quarks. Okay. So the gluons are interacting, but they do participate in a way. So they are not very pure as mediators in that sense. So general relativity, gauge theory concepts also appear in general relativity. So having general covariance principle as a gauge invariance type. So applying gauge theory to relativity and gauge theory to quantum mechanics, somehow you can bring them together. That's the idea of invariant fields and things like that. As an invariant field theory, if you want to look at it. Some alternative theory of gravity, like gauge theory gravity, explicitly use gauge principles. So classical gauge fields. So can we bring again back to the classical aspect, which is measurable aspect? That's a highest goal of the gauge theory. Mathematical framework. The mathematical framework of gauge theory involves Lie groups and Lie algebra. Like I mentioned the previous episode about the Lie groups and the Lie algebra, special property of symmetry, quantifying symmetries of the fields. Lagrangian of the system is constructed to be invariant. So Lagrangian essentially describes the energy, the equation, helps to describe the equation of motion. Uh, and they're invariant. So that's very important. Uh, the transformation itself should not affect itself, right? So that's the idea. Classical field theory. The classical field theory, gauge fields can be described using differential geometry and fiber bundles. So the approach provides a geometric interpretation of gauge invariance interaction. So again, if we bring the classical field towards the quantum mechanics and general relativity, and the quantum mechanics and general relativity towards the classical, somehow we can find a happy medium, hopefully, where they unify. That's the idea. Loop gravity space-time localization matrix. So loop gravity, the quantization of space-time, LQG, or the loop quantum gravity, is quantized smaller scales, discrete structure than continuous. Often visualize a network of loops known to be spin networks. So it's based on the spin aspects of the particles, uh, which became the key aspect to describe. And then in all the quantum computing, we have the spin up or down, and the superposition and all these uses a spin property. The spin networks. These are graphs where edges represent gauge field quantum state. So going to details, I'm not going to details of these, but uh, I there are a lot of references at the end of this episode that we can refer to that to get more understanding uh, of this how these geometrically come about. The nodes represent interaction between the states. The spin networks help to quantify geometry of space in quantum network. Uh, so quantum states are the edges, and the interactions uh, between these states are the nodes. So in simple way, space-time localization aspect, discrete geometry. In LQG, geometry of space-time is described by discrete structures which are tiny chunks or contour space. So you have contour space. Nature helps avoid infinities there. So renormalization, avoiding you know, infinity is fundamental theory. I mean, that's a fundamental problem with the classical physics that we saw ultraviolet cutoff stuff where temperature goes to infinity, which is not possible, right? Uh, a ridiculous thing. So all these are problems, and then we have the later on the vacuum catastrophe where we have the energy density of vacuum itself becoming too high and very different from that many ridiculous order of magnitude between theory and experiment. But boundary maps then in LQG explored concept of boundary maps where quantum states of the bulk geometry are presented as wave functions on the boundary. Like I said, the information you can obtain from the boundary, like the conformal field theory. To understand relationship between bulk and boundary, like I said, adds or anti de Sitter space versus de Sitter space and the bulk and the surface states, the boundary maps, try to bring together that. Matrix model, alternative approach. Matrix models offer alternative approach. So they are the matrix aspect, which eventually became part of the M theory, providing different perspective quantum gravity, quantized cosmological space-time. Certain solutions matrix models suggest quantized cosmological space-time. Fluctuations of matrix can give rise to gravitation. So the idea is that they are all matrix, and the fluctuations, localized fluctuations, they create a gravitation phenomenon, and that's being explored now. Connections and implications. Bulk boundary correspondence. The idea that bulk properties of space-time can be understood through its boundary, significant concept. So we are bringing to the history aspect, so you don't want to miss these important things before we get into M theory. And unfortunately, I'm not able to bring, and hopefully the next episode bring more the M theory aspect. But these are very important elements that we have to examine. So that leads to why the M theory came to being. Again, we have to establish that. So hopefully this episode will be one such things that eventually, we can, if you want, we can look back on this episode. So then we can move on to the contemporary history or emergent theories. The correspondence is crucial for understanding quantum states of geometry relate to observable phenomena. So the quantum states of geometry are there. This is what conclusion or the gist of these are. And then we connect that with the observable phenomena. Actually, we observe what we observe. So emergent properties. The LQGN matrix model suggests space-time and gravity might be emergent properties arising from deeper fundamental quantum structures. What are these structures? That's what they examine. So thank you very much. I'm not able to spend much time on the M theories, but we hope to do that. How the matrix modeling come to M brains and applicable to vacuum or entity environment. That's what we want to go on from 9th and 10th episode. So we'll concentrate more on those aspects, the M theories. So the references are, because of the Bell aspect, I am not able to spend time on the M theory because that's a very important part of the quantum theory. So we have many references, quantum locality, and then Bell non-locality, EPR, that Einstein came to be, Podolsky's non-locality, and the hidden variables, things like that are there. The Schrodinger paradox, non-locality, then the reality probability. So these are important. Experimental test by Alan Aspect, the others. Bell inequality of experiments. Then local realism, the high energy physics of the entanglement aspect, the non-locality, photonic quantum network, the holographic principle, I mentioned about that, quantum gravity, loop quantum gravity in space-time, quantum gravity, 30% quantum information. These are becoming important. Electroweak unification, like I mentioned. Electroweak theory itself, certain, and the particle physics, the electrounification, W and Z boson, Higgs mechanism, Higgs boson, then Higgs boson, the Hunt discovery structure of future, then the editors, then you have the particle physics aspect, nuclear, the big idea of unification. strong force, the quantum chromodynamics, quark confinement, chiral symmetry. Again, chirality, I didn't talk much about that, but that's another aspect that's very important. That describes about the asymmetry is one of the key aspects between elementary physics and nuclear physics. Emergent gravity, will it rewrite physics? Space-time emergent phenomena, entangled particles. So idea is that there is an idea that gravity essentially is a you know essentially is eternally entangled particles. The idea eternally entangled particles maybe what's contributing to. But we can think of that in terms of a monopoles. You know, uh, they're eternally entangled by the forming a dipole, and then that we know uh, the Maxwell theory and also uh, the idea that particles cannot, I mean, ca- they cannot be a monopole, aspect. Uh, so the emergence of gravity in framework of emergent quantum mechanics, then the classical gauge field theories, the classical gauge fixing quantum field theory, quantum. So we are trying to pull out some measurables, some observables and measurables, I would say. So look at boundary max, like I said, the conformal field theory where it talks about the boundary aspects. Space-time come in tiny chunks. That's the aspect of loop quantum gravity. Quantum space-time gravity in matrix models. In loop quantum gravity, beyond space-time, the foundation quantum gravity. Rovelli is one of the key persons these days who is trying to really unify with the quantum gravity and able to define the conditions. So thank you very much for everything. And then I would like to welcome further discussions on that. Unfortunately, I couldn't spend much time on the you know the actual M theory per se, but it is a next step. But these are very important elements. So I thought that especially the Bella aspect is what uh, you know pulled me away from the describe the M theory in this episode. But I think the next episode definitely that's the next one. No question about the brain theory and theory.
Well, very good. Well
Thank
done.
you very much. Thank
Uh,
you.
I liked all your references at the end. The looks like some good resources there, maybe to look into and check out. So,
Thank
well, do you want to go back to your original slide?
Yeah, I can go back there.
So, from beginning here.
Again.
So yeah, it was the bit of false advertisement there, Rajan. You said this was going to be about M theory. Didn't
Yeah,
see any. There was no M theory in there at all. Oh, Rajan, you frozen. Right, you might want to log out and come back in again, maybe.
Oh, Christopher, something happened suddenly.
Yeah, you froze. Maybe your
Yeah.
computer got overloaded or something. I don't know. Or I
Uh,
suppose it was more likely to do with the. I don't know. It seemed like
let
when you were starting back up your slideshow, you kind of froze.
something.
You were
Yeah. So
in the
something happened.
middle of responding to the false advertising accusation.
Oh, sorry. Uh, yeah.
So yeah, you want to.
Yeah. Initially, I thought that, but the Bell theorem actually, I should have mentioned that. Uh,
Yeah,
I
it's a good
didn't check
one.
back
Yeah.
because, sorry, but I didn't put in the title about M theory. But when I talked,
Oh yeah.
I think last time when we talked about last time in that in our earlier episode when you were just discussing that I mentioned the eighth episode will talk about M theory, but actually, yeah, sorry.
Maybe the next
But the
episode.
ninth episode definitely will be M theory. Yeah,
Okay, and
episode.
then what's the final?
The
The
final will be the emergent theory.
Oh, kind of more to do with contemporary stuff. Is that what you were saying?
Contemporary things that talks about
So
uh,
basically, what's you'll be looking at what's going on now, is it roughly?
yeah, in a way we won't, it'll basically touch up our you know uh, research or our publications in some sense, but not too much because in the history we cannot still talk about our theory which is not fully encompassed by or proven, or other people are not really totally you know
Aware
uh,
of it, or even yeah, it hasn't been
yeah,
peer
we,
reviewed.
we have to still go a little bit more before
Yeah, you could
before
mention
it
it, but
becomes
mainly you'd
just
be talking
mentioned.
about what? Because yeah, because a lot of the things that you're talking about are kind of they've been around for maybe a couple of decades, but they're also a lot of them
Yeah,
are still considered fairly contemporary in some level, aren't they? People are
but one
still
of
talking
things, yeah,
about
one of things,
gravity.
yeah, yeah, one of things is a numerical relativity that you talked about briefly. We can
Oh yeah,
definitely talk about that. That will be part of the emergent or contemporary physics because the numerical thing is came only now. So that's definitely a topic. So in 10th episode we'll have numerical relativity. Ninth episode will be emphasized on M theory. 10th episode on numerical relativity. In a
oh,
very simple.
so why is numerical relativity only emerging now? Why wouldn't it be? You'd imagine is it just because computers have gotten better, or
Yeah, the computers and also the discrete aspect will mean that we are talking about. I talk okay here we talk about discrete aspects, right?
yeah?
Uh, we talk about a loop quantum gravity, things like that. The discrete aspect, discrete structures based on Planck. So numerical relativity will help in that because numerical aspects are essentially discretizing, like even Fourier transform. You can discretize Fourier transform, and you can produce, uh, each one is a different, you know, structure that is numerically different from other. So we can, if it is discrete, we can always count them, right? So and you can count them; they are numerical. So the very simple math from that simple math that you're talking about. If everything is continuous, right? So how do you describe numerical? How do you attach numerical values to them? But if they
Well,
are
that's it.
discrete,
Yeah, that's the great contradiction, isn't it? Of the you have
yeah,
in general relativity has to be smooth and
yes,
continuous, but then if you're going to
yeah,
transform that into a computation, there's going to be some discrete values there, sort of inevitable. That's
yes,
okay. You could just say, well, you're doing it down to a certain
yeah,
resolution or something,
yes, yes. The
and
Planck scale.
resolution
That
could obviously be very high if you use a lot of data points, which
yes,
would require like a supercomputer or something on that
uh-huh.
booster computer. So yeah, so you started here talking about Bell's non-locality because I've done a bit of research into that, but
This
yeah,
one. Okay.
yeah, that's the one. so the Bell's theorem and entangled states. Because when I was first looking into that, I was kind of thinking about it from the point of view of the polarizing filters, and you put one in
Mm.
at different angles and things like that. But then, as you mentioned, EPR paradox,
Yeah.
which is Iceland, Podolsky, Rosen. So they came out with a paper talking
Uh,
about entangled. You see, this is where I get confused. Well, I get confused all over the place on this issue, but this is, I suppose, one of the beginnings of my confusion is I think they say that this is like the seminal paper, you know, the one that started it all,
mm.
talking about entanglement, um, you know, hidden variables and all of this.
Yes.
But that
Mhm.
confuses me though. So it's as if they're how do you say, attributing quantum entanglement and all of these ideas to Einstein. So he becomes the father of that kind of notion. But that confuses me though, because he's coming out saying entanglement isn't real. You know, it's spooky action at a distance, and that the whole thing is explained via um, via hidden variables, because otherwise it would violate relativity, which seems very valid. I mean, you know, he's come up with this whole theory of relativity. Uh, Nothing can travel at the faster than the speed of light. So when someone comes up with, or well, obviously entanglement was considered by some other person, and then present. Well, I don't think it was demonstrated until later, but from the maths, it was obvious, and then that implied you know, faster than light transmission, so that would violate his theory. So that's what's confusing me, because I don't see why he like. Well, I suppose if he was researching the maths and he could see that that was what it was saying. Yeah, it just strikes me a bit as a bit odd that, you know, normally you're a researcher, if your first paper is coming out saying this concept is wrong, then generally you're not the one that originated the concept. You're instead replying to someone else's research, and you know, because the first person posits entanglement and faster than light um, communication, presumably, and then Einstein would say no, it's more hidden variables. So you know, so I think it's a bit odd that that's for some reason that is I guess he was the first to write a paper on it, but it's like a paper rebutting someone else's work. So probably I know Schrodinger was involved. He came up with the name entanglement. So I think if we're going to discuss entanglement, it'd probably be Bohr or Schrodinger, you
Mhm.
know, in terms of this. But having said that, if I mean, you have this non-locality thing, and then so I guess the question I'm thinking then is, I'm a bit confused about what Einstein's talking about with hidden variables. Let's say I have a particle on one side of the universe and it's spin up, and then I have another particle on the other side of the universe, and we know instantly that one is spin down because this one's spin up because they're entangled. Sorry, yeah, should have mentioned.
Mhm.
Okay, so the way I'm thinking about hidden variables is like, it sounds very mathematical, doesn't it? So you just think of like a bracket or like a vector, and for the spin up you have like a one in the top, um, you know, a x
Mhm.
first index, and then a zero on the bottom one, and for the other particle it's the other way around. So and then, you know, so there's a hidden variable of a zero and a one and a zero on the other side, and then when you make a measurement on one, it's, you know, it alters that state, um, and because I just like hidden variable. It's not very it's a very mathematical term. It doesn't really give you any idea of what they're talking about. You know, because even if you like, do you know what I mean? Like,
Mhm.
what is a hidden variable?
Yeah. So one of the things I feel that there are two aspects. Understand? I don't know whether this is a outright thinking. whether he was in a way contradicting himself in some ways. Also, he was trying to reconcile between the classical physics and things like and relativistic and the quantum physics. So he
Well,
was
I
trying
assume,
to
I assume there was a discussion going on between Bohr, Schrodinger, Einstein, and all of that in conferences and or what, however the discussion was going on, and people were finding different things, and then he must have been the first person to write the paper. But yeah, it's a strange one. Presumably he was in the mix with all of them discussing it. So, you know, yeah, I just think the idea of like ascribing the concept of entanglement, which he disagrees with, to Einstein is a ridiculous concept. So but that's like neither here nor there. The thing I'm interested in is what he means by a hidden variable, because it's repeated all the time as if it explains itself. But I don't know if it does, because well, I mean, it clearly doesn't, because I don't really follow it. So you have like this, like I was saying, like let's say you have a 1 and a 0. So these are the variables attached to one particle would spin up, and then a 0 and a 1, and those are variables attached to another particle. And these are we haven't observed them yet. So maybe they're hidden in that sense, because we haven't made the detection yet. Then we make the detection, and then we know for certain that this one is spin up. And because we know that, therefore we know the other one is spin down. So in some sense, it's just like what they're really talking about is just detection, right? Is that what they're talking about when they say
well
just mean
actually you are going a little bit further, but when you pull back, the actual hidden variable is that locally something is affecting the dynamics. It's nothing to do with the global thing. Locally something is changing. That's a classical thing, right?
Okay, that's an interesting point. But what if the two particles
that's
are separated by like the other side? How is it a local thing then? I don't understand.
That falsifies. Yeah, that falsifies the hidden variable automatically. If there is a,
but that is the whole point, isn't it? Like entanglement
non-locality.
So is he saying? So are you saying that Einstein, when he mentions hidden variables and local, what did you say? Local causality or something like that?
Yes.
So basically, he's saying that we will only see this quantum effect at when the particles are close together. But if they get far enough away, you won't see it.
In a way, yeah, that's a good way to put it. Yes.
So that's what he's saying. So he disputes this idea. So have they ever done? So are you saying that they've never done a quantum entanglement experiment on Earth, separated by a distance? So we cannot get far enough away, can we? Like one.
Well,
it's too difficult to do. Is this?
No, Alain Aspect actually has done that, right? With the polarizers, he did have on Earth lab experiments. Of content with the polarizers. He said one photon is entangled with another photon. And then he measured them. So these are entangled photons, and he proved that they can communicate.
Faster than light. Okay, so doesn't that disprove Einstein's whole point then? That should be just the end of it.
Well, it's the question. He didn't mention about faster than speed of light. See, Alain Aspect said that they can communicate with it.
Is that not the crux?
Implied. That's implied. Yeah, you can say that's implicit. That's implicit.
So that is the thing that needs to be proved, and if that hasn't been proved,
no.
So then why are we wasting time with all of this Bell's inequality? Like, what tests are they doing for Bell's inequality? Like, why not not do the test? I suppose it's just difficult to do, is it? And that's why they haven't done it, because technically it's just very difficult to do.
It could be high energy. Yeah, it could be high energy. You need probably high energy. Yeah.
Yeah. Also, So okay, so that's fine. So maybe then Bell's inequality, a test for that is more you know, it's more efficient. They can do this test, and then they can prove whether or not hidden variables exist, and then that has a knock-on effect of proving Bell or Einstein right. Okay, so that seems, or sure, yeah, whatever. Okay, so yes, I mean there's some other aspects like you know, this light polarizing thing. You send light through a polarizer, and then you have another one at a certain angle, and then another one like this. And that was often the experiment I would think about when I think about Bell's inequality theorem. But like, if you think about that, that's all very local, because the the filter is, they're all very close to each other. But if you're to spread the filters out, so the light goes through one, gets polarized, then goes through another, and then goes through another filter that's like on the other side of the universe or something, maybe not that far, but far enough away. And then you're in the middle, and you just put a polarizer in. Well, that's not going to affect the light that's coming out of the further polarizer until the newly polarized light presumably reaches it. So I don't think that has anything to do with local causality or whatever. So in that sense, I don't really see the connection between the polarization experiment that I just mentioned and what you're talking about, or what, you know, the whole thing, because it seems like you've some amount of light, the amount of light coming out of the polarizer goes down. You have a polarizer at 45 degree angles. The light goes down again. But when you put one in at like between 45 and 90, you get more light comes out. So what can we deduce from that? That somehow, what are we deducing from that? That there's how are hidden variables to play in that, or how is
See, one of the things is that I think that entangled one of question, and this is a perplexing things, or what you call a paradox, in a sense that if we have entanglement, the question of propagation does not have much meaning. See, the classical physics says that something produces and then it propagates, right? That's the idea hidden variable also, that luckily something is changing and that propagates, that wave, the light, whatever, propagates. But the entangled means there is no need for propagation. It's instantaneous, that if the spin up here, immediately it spins down. There is no question of propagation. This is an instantaneous effect. So the question of propagation itself is brought into question in the aspect of entanglement or non-locality approach. So locality approach does require hidden variable. Locality approach uses hidden variable require a propagation, okay, automatically, because it's produced. But the non-locality or the entanglement aspect does not really require a propagation aspect. So
that's the crux of the matter then, I guess.
Yeah.
Well, that's very interesting. So I had a few other points to make. Well, did you see the email sent by Emmanuel about Bell's? He had some video posted about an American guy who apparently, using his computer and multiple simulations, showed that hidden variables do exist and that Bell's inequality is wrong. Did you see that video?
Not yet. I saw one of them, but not the other one. So see, I didn't reply to that. I had to find a time to see that video.
Yeah, it's like 50. It's 50 minutes long, I think, or it's quite long. Like, I'm not too well versed on the whole thing. I know that Bell did there's a very simple, how would you say, a very simple explanation of Bell's inequality theorem. I think it's using like 3 coins, and you can figure out like whether it's heads or tails or heads or something, and then you do it must be like the measurements and then the outcomes. and so you have all these different permutations, and then that gives you a probability of like, I can't remember what it is, 3/5 or whatever. And then, so then if you do these experiments and you get a different probability, then that disproves hidden variables somehow. And instead of this nice smooth curve, you get what they have been getting for the last while, which is some sort of blocky curve. And so you read that, you go, oh, well, I can kind of follow that. That's simple enough logic. But when you really dig into that, what does any of that mean? And when you start looking more into Bell's actual equations, they get very complicated very quickly with a lot of logic. I don't know what you call this, logical statements and probabilities that are kind of all nested. So he doesn't seem to be using this very simple model that is usually how it is explained. And more to the point, how does this even translate into this curve that we're talking about? It seems like it's some sort of statistical thing where you run multiple experiments over and over and over again. And if they fit on this Bell curve, that's what I was trying to say earlier, then no hidden variables. Now, presumably, usually when you see a Bell curve, you're thinking, okay, it's all random, isn't it? It's all chance. But maybe if you're seeing some other kind of distribution which is more angular, then there's something throwing it off, which would be maybe a more instantaneous thing. Or so that's a bit confusing. So like I say, I watched the entire video. I didn't really understand any of it on a deep level. Like on a very surface level, I could nod my head and go, okay, yeah, sounds good. But the thing that I'm curious about is, like, he's saying, oh, you know, that they've been doing this experiment, Bell's inequality theorem experiment, repeatedly over and over again for, like, I don't know how many decades, right? And they keep getting the same answer. And then he's doing it himself on a computer, presumably simulating it rather than actually doing the experiment. Presumably there's an actual experiment you can do. So, and he's getting different results. And he's saying that the whole thing has been, well, what I can understand, it seems to be that he's saying that the whole thing is some sort of misinterpretation of the mathematics and what hidden variables meant and blah, blah, blah. But that seems very strange to me, because that would imply that there's just a fundamental disconnect, like a fundamental misunderstanding about, like, something that should be very basic, like an observable. So we have an observable, it comes out on the line. But then if you have this somehow fundamental misunderstanding of what you're doing, and that alters how you process the data, so you get this jagged curve instead, and this occurred just because you were following Bell's inequality theorem, which had some misconception about you know, non-local causality or whatever. You see what I'm trying to say? It's like,
yeah,
how could someone's misconception of reality alter the results of what should be an objective experiment? You know, and like, it almost sounds like a quantum experiment in itself. And in between, you have these researchers who are trying to establish some truth, but because they don't know what's true or not, there's this sort of hidden variable thing. And then, but what I'm arguing here is that I don't accept that as, you know, I wouldn't accept that as an answer either. You know, the universe either has, like, it's either a yes or a no. You run the experiment, you're going to get a result. It doesn't matter if you know what I'm saying? It's like, if you, just because you misunderstand fundamentally on a theoretic level what's going on, shouldn't make a difference to what the results of the experiment are. Because usually that's how we work, isn't it, in science and in quantum mechanics especially, because we don't know a lot what's going on. You have the experimental results first. Obviously not all, like, there's a lot of theory that comes first, but let's say a lot of the time we'll have, like, some empirical thing, like, so here's the results of the experiment. work backwards to fit your equations to that, and that's a valid way of working. But so do you get what I'm saying? There seems to be two different opposing answers here, and so
one of the things is that I think Bell himself changes positions. 1964, when he started 1964 versus when in 1960 he started thinking differently, you know. So
well,
that's a very
what was his conclusion? Because I remember speaking to someone, and I've heard it said before that this whole thing about local, or I guess the opposite is global, and although they okay, so that it was like all this thing about maybe Bell's inequality saying that local variables don't exist or something, but then it was actually no, he was saying that was what he was saying. He was saying that local variables do exist. It's like, okay, well, what does that mean?
It's a contradiction. It's a contradiction.
But you're saying that later on in life he contradicted himself, or he went back on something. Is that the thing that he went back on, that specific thing, or was it something else?
See, the casualty aspect, I think he had difficulty dealing with that.
Which
local causality. Causality. Sorry, causality. Yeah. I don't know whether you are confusing with the casuality or not. But
he had a problem with being casual in local places.
Yeah. So causality and casuality. Maybe he's trying to brainstorm between causality and casuality, and he got a problem of reconciling. It's quite it's quite possible.
Okay, there's a bit of a superposition going on between being casual and being causal. Anyway, so he had a problem with local causality, which you have here in brackets is local realism. So he's saying that maybe things aren't real on a local level, or well, I suppose he's not saying that they're not real. It's like that locally you could have this like faster than light travel, is it? But then globally you wouldn't have it. But then but why not? Because like if it's faster than light, it wouldn't care if the two particles are either opposite ends of the universe or right next to each other. It would just be instantaneous anyway. So who cares about local or global at that point when you're talking about instantaneous? See what I mean?
It's the propagation aspect. I think
if they've been talking about this for decades and they haven't even, and I've been looking into this for maybe 2 years, not like every day or anything, but now and again when it crosses my path. I still don't know what they're talking about, to be quite honest with you.
See, I did a Mendel experiment recently, and there is I found that there are two thoughts of thought. I analyze my own thoughts, and there are two ways of looking at it. One of them is locally, you cannot, it's some eternal, it could be, I don't know, it's alien or whatever. And that information comes superlunar speed, the local level, right? It's faster than speed of light. But then what happens is immediately when it propagates, it's like a vacuum around, it propagates the speed of light. So it immediately reduces the local, like a Planck scale like thing, or something like that, or it could be a thing. That's instantaneous. But then when it propagates like a special theory relativity.
Well, I would have, obviously that's your thinking on it, and that's valid. I think that's interesting. But I mean, I have an issue, it contradicts what you said earlier about the crux of the matter being either instantaneous or propagation. It's either one or the other.
So
wait, if it's instantaneous, then there's no propagation. And so that's just not right, Rajan. And I would
but let me clarify that.
You're saying that, and I don't think they are. And in fact, I've never heard anyone say that or even get close to an explanation as understandable as what you just gave. At least if they did that, I could respond and say, well, okay, obviously more work needs to be done because that doesn't make any sense, or, whatever. Unless they are saying that, because I wouldn't put stock as an explanation.
No. The following way. Let me clarify that. Information creation versus information propagation. Okay, so information creation could
So
be,
you're going into, so it's more information theory that you're going into, but I don't
yeah,
think that like Bell when he was, or
yeah,
any of
yeah,
the physicists
yeah,
working on entanglement originally, you know,
yeah.
they didn't know or think about information theory. That came along later when people were trying to come up with an idea of, oh well, how is this information being communicated between the two um, particles faster than light? Well, okay, information doesn't have any mass, so it can travel faster than the speed of light. And that's a solution, but that is not, that is very much a theory. It's we've like there could be some truth to the idea that information just exists as a, what would you call it, a reified kind of entity in the universe. I've no problem with that, and it may propagate or may travel. It may be instantaneous, superluminal, but it might not. It might have like nothing to do with the quantum entanglement aspect. It's just,
Mm.
well, it's, you could just say God did it. That would be another
Mhm.
valid thing, but we just don't. Um, it it's not necessary like, I mean, information theory is what's the difference between God and information theory? I don't see a difference between those two things. Okay, so not that I don't have a problem with God or information theory
Mhm.
or unifying information theory and God. That's fine. I'm just saying that more than likely, when the physicists are talking about quantum entanglement and some method of instant communication, they're talking about some physical thing they want to get across, and
There could
you know,
be two paths. One is a superluminal path. The other one is the subluminal path. So superluminal path, maybe like worm or whatever, they instantaneously, like a spin up, spin down. Uh, that path, when it goes through that path, if it changes the spin here, it immediately changes spin here. So that's
yeah.
a superluminal path. But the actual thing, once it creates the locally, then it starts propagating. That propagation occurs at speed of light or even lower
Well,
as it goes.
unless we have any experimental data, there's just no point in talking about this, because if they haven't
No,
conducted
no,
the
we know
if they
in
haven't conducted
explaining.
the experiment at further distances and shown that there's this delay that you're talking about, because
No,
no
no,
one's ever mentioned that. The whole point about entanglement is that it's instantaneous. That's the thing
yeah,
that needs to be explained. And the
yeah,
explanation that Einstein is giving is something about local variables. Now,
yeah,
those local variables must be local to each particle, but
yeah.
um, somehow able to transmit the information across vast distances in order for it to be an explanation of the very thing that not thing, a very natural sort of
Mhm.
observation that we're observing. I
Yeah.
didn't say that
See,
very eloquently, sorry, but you get the idea. So either there's a thing that we're trying to explain, which is this instantaneous action.
mhm.
So maybe if we've actually proven that that is a thing, and then we have, so I don't think Einstein was alive to see that experiment done. And if he was probably quite old. I don't know when he died, but
1955. Yeah,
right. So he wasn't alive, I don't think. When did Alan Aspect? Oh, 80s. Anyway, yeah.
yeah,
So he wasn't alive to see that, but presumably, the math was saying that this happens, so they must have accepted it on that level. So his solution, the thing that would make it so that his theory was still correct, which presumably it is, was this hidden variables thing. But
mhm.
I don't even like, that's not even a good explanation to me, because it doesn't mean anything. Now, if he'd said like what you said, oh, there's a wormhole that connects them through a higher dimensional space, and that space is closer together, so everything is, it's like folded, and so that instantaneous. That's a valid explanation. a ridiculous explanation because we have no evidence of such a thing, but it's still a better explanation than just saying, oh, hidden variables. You might as well have just said, oh, quadratic formula. It just doesn't mean anything. It's just like, to the average person, it means nothing. And I'm wondering if it means anything to scientists either. So do you want to move on to the next slide?
Okay.
Because I think we've beaten this to death. And, you know, someone watching this video,
I mean, they're not. No, I think nobody is very clear about it. So we are not allowed.
Yes, yeah, I'm sure. And actually, I wouldn't be surprised if someone came along in the comments and said, hey, this is what it means, because I'm sure it's just going to be more obfuscation.
I don't think anybody really has figured out completely. Yeah, I don't think anybody has really figured out what exactly, which one is completely correct. Is a hidden variable correct or non-locality correct?
Well, it's not even, that's not even the issue, is like, what even does hidden variables mean? Like, what is it trying to get at? You're talking about a wormhole? It's not even clear. Yeah. It sounds like what you're talking about is some sort of information theory, because it's so abstract and so in the world of like mathematical equations and information that it must be talking about information theory. But I don't think was Einstein even aware of the solution of information theory at the time? Or, you know, that would have come along much
now it's emergent. It's an emergent theory now.
What's an emergent? Oh, you think it's a new contemporary theory?
Yeah, information theory.
I mean, information theory is very new. Or it sounds pretty new anyway. I mean, obviously I wasn't alive back in Einstein's time, so I'm not sure if it was knocking around back then. But it doesn't, like, just from
computers.
Kind of
computers were coming up during that time, but it has not established.
Yeah. You know, I mean, we might have to look into that, but I agree with you. I don't think it was around in Einstein's time. So when he's talking about hidden variables, he's not talking about information theory, unless it's like as kind of a subset of that. But even so, I mean, information theory is positing that the transmission of the information or whatever is happening superluminal or instantaneously. So if Einstein's theory and information theory are the same ultimately, or then Einstein is saying that there is instantaneous transmission of information. He's at least alluding to that, or admitting to that. Whether or not he says that there's another explanation, I don't know. Nobody knows. So I'm not even sure why Einstein's name's being mentioned in connection to this, because, okay, he's the one positing that this can't be real, and giving some other theory which physicists are testing, so they must know what it is. But at the same time, according to this other guy, the whole thing that they thought it was, so he's agreeing with Einstein, which I think makes sense. But they're thinking, oh, there's, you know, it was all just a misunderstanding on the physicist's part, that they were thinking about the whole thing the wrong way, and that altered the results of their experiments, which I like. That in itself would be like a defeater to science as a whole, wouldn't it? Because it would mean that we can like make an experiment and the result is based on what we think the result is going to be. So that would be useless. So they can't be saying that. So they must be saying something else. But if I can't even understand that level of like where we are at with this experiment, then I'm not even going to begin to try and understand the more delicate minutiae of the subject at this point, if you get me. So I think we should move on. Okay, so classical physics and locality. Forces propagate. This is, you had a nice bit on the holographic principle. That was interesting. Duality needs a higher dimensional. Yeah, space-time. Okay, I don't think I really have anything to add to any of this. It's all quite straightforward.
Okay.
So the next slide is what? Oh yeah, this was good as well. A lot of information here. Key concepts. I mean, the Weinberg angle is another perplexing thing, isn't it?
Yeah.
So you have this mixing. So let's say you have a I mean, kind
You
of
have done some work on this, right? You have done some work on this WC boson.
yes,
You are
yes,
trying to
yes,
do.
a little. Yeah, I've done a little bit, and I've looked into the mathematics, but there's something about the maths that's okay. It's all very logical. It's all very step by step, but it kind of doesn't give you the sense of what's going on. Like if I knock a glass off the table, it's going to smash on the ground. Let's say if it has enough force, and that is a real physical event that's happening. Now, presumably, if you have some sort of symmetry breaking that's going on in the early universe, that is also a real physical event that's occurring within some sort of field. And if we had the right kind of goggles or something, we could look at that and we could see, oh, it happened. It broke. So, but if I were to describe the glass falling off the table and smashing in a bewildering amount of equations and fucking matrices and coupling constants and fucking Weinberg angles, and no one had a fucking.
Have you looked to Weinberg angle?
Talking about it, right? And no one would care either to even like. Just like, what happened? Glass fell off the table. It smashed. Oh, I get it. Okay, so explain this to me in similar terms. Nah, it can't be done. Just accept what we've written. Well, that's the difference between like understanding something on one level and understanding it on another. And I think we can get like so far with the equations. I think where they're good is in determining the outcomes of certain experiments. Like if you were to fire an electron at an atom or something, what way is it going to scatter? Okay, that's good. And I suppose it's to do with forces and how those forces act on a particle, and those forces including maybe the weak force and the electromagnetic force. So then there's a shift between where one is ascendant and the other is ascendant or something. And that happens presumably at some sort of mixing angle, which is the Weinberg angle. But where in space is this angle actually orientated? Because space has no up or down, yeah? So is it like 23 degrees to north? So it's obviously, it's an angle with respect to an axis in some sort of spin space, like the x plus w, sorry, what am I saying? W plus W minus, that's an axis, right? It goes from like +1, -1. And then we have so that's X, Y, and then Z is not the Z boson, actually. It's the electron, or the photon, sorry. So maybe the mixing angle then, excuse me, is some sort of vector within that space that's tilted at 23 degrees and points to the position of the Z boson within the whole space.
Is that a Hilbert space?
Sorry?
Is it a Hilbert space?
It is.
Or the vectors?
It is not a Hilbert. I don't think it could be a Hilbert space, could it? Because maybe because it only contains one particle, which is the Z boson. So it doesn't need to be a Hilbert space.
And but it's a vector space. Is it a vector space?
I think it's a vector space, yeah. So anyway, so that's my thinking. Maybe the Weinberg angle is that. But why would it? So, but presumably the Z boson can move around within that space. It's not stuck at that angle. So anyway, that's about as much as I want to say on that issue, or that I even can say on it. So we'll move on. Again, anyone in the comments want to shed light on any of this stuff, please do.
The next slide.
Also, apologies for the expletives there. I was getting a bit.
No. Okay. If you can edit that, no, it's okay.
Not a chance.
I hear this all the time. I mean, you can just distribute it. I mean, you can distribute it and say when you expand it, it doesn't for farce or something like that. Particle.
Yeah. Take the dot product of that. And, yeah. Okay, let's continue on. So experimental. Okay, so this was good. You're really just how to say, you're summarizing all of these complicated issues in like very simple terms, which is good. People can understand it. Confinement, asymptotic freedom. Oh yeah, that's part of the whole gluon thing, isn't it?
Yeah.
Direct weakly proper. Yeah, that's true. Particle physics, nuclear physics, high energy. Okay, I think we can move on from this. Yeah, so I think the main things were kind of discussed. Although there's some interesting things here. Eric Verlinde, obviously, with the whole entropic gravity.
Yeah, the idea of the localization of the gravity. See, the question is, so is gravity determined by the hidden variables? That's the whole thing. Locality,
Right.
causality,
That's what we're
local
talking about.
causality.
Yeah, that's interesting, isn't it? Because when we talk
Yeah,
about hidden variables within, like let's say entropy or temperature or something, right? Because
yeah,
temperature and entropy are very connected. So
ensemble. Yeah,
right, so maybe that's the answer to the question in the earlier part of this question and answer session. Let's just call it that. Excuse me. So we have a system, yeah, that has a lot of particles in it, and they're all bouncing off each other. So it's hot and it's what, high entropy, right?
mm-hmm.
Right. So as this system cools down, let's say, and it doesn't even have to be particles; it could just be like a field. But as it cools down, as it dissipates, um, the particles stop bouncing into each other as much. So they have less degrees of freedom because they're not going to bounce in well, let's just say they have less degrees of freedom. So they start moving in less erratic ways, and so the number of degrees of freedom appears to go down. Even though, potentially, like if a particle comes in like this, then they're going to bounce away. But if they'd come in a different way, they would have bounced in a different way. So I think that the degrees of freedom are still there, but they're probably constrained by the particles and the fact that they're on determined paths based on their previous interactions. So as the system cools down, we're going to have less possible degrees of freedom in each case separately based on the initial conditions of the system. And so we could say that those other degrees of freedom that we've lost are now not really lost, they're just hidden. And so these are hidden variables of the system. And so if we're then to take that and transport it over to the entanglement thing, maybe we're saying that when the two particles get entangled, they lose some degree of freedom. They now, because they're dependent on each other for their degrees of freedom. But there's other states, hidden degrees of freedom, that allow them to move in a different way, and that would be a measurement or a decoherence or something. Okay, that sounds more scientific, doesn't it, as an answer?
Yeah,
But
excellent. You are a Professor O'Neill now. You're Professor O'Neill. You are, when I listened to a lecture about thermodynamics in my undergraduate, I had professors, right? You sound exactly like that, So it makes a lot of sense because kinetic theory of gases is essentially based on what you are exactly describing, what a kinetic theory of gases says, that mean free path and all that, how they derive the 8 pi m cubed, that how they derive the temperature, the Boltzmann thing, from the kinetic theory of gases, the very fundamental thing. I think what you're describing is exactly that.
Okay, and that's got to be local, doesn't it? That whole thing, because we're talking about, so the degrees of these hidden variables are local things. So they have to be in the system. So that presumably then, like you were saying, couldn't be. We would assume that as they get further and further away, that the degrees of freedom increase then, and they become disentangled.
Yeah.
So right.
Yeah. So when it entangles, you are right. I mean, the degree of freedom get constrained. It get reduced. Yeah, automatically.
Okay, so that's very interesting. That's actually quite a beautiful.
Yeah, that's something you can work on. That's something I think is solid. It's a solid concept.
Yeah, and I mean, there's a lot here. So then we can go back to Verlinde's work with
Yeah.
temperature emerges from. Yeah, so I suppose we did touch on that, but there's obviously more to say on that aspect because it's hidden stuff within entropy. And then of course you have the same thing with, it goes all the way back to Planck's work. Essentially,
Oh yeah.
it's all Planck's equation there. So it's amazing, really. It's amazing that they aren't talking about Planck all the time.
Oh yeah. I mean, how do you Planck and the thermodynamics come together? That will be a big thing,
Oh,
Uh,
but surely, like black body spectrum radio, like it is all just
yeah,
thermodynamic. So yeah,
yeah.
they haven't really moved on from this point. It's fascinating. It seems to overarch many of the things. So let's move on. Okay, we talked about that source sync dynamics. Oh no, okay,
Oh,
sorry. I just meant move on to the
okay.
next paragraph.
Oh, okay, okay, okay.
Source syncs added, removed. Oh yes, of course. Right. Okay. And loop quantum gravity. Now I was wondering, discrete structure. Yeah, because isn't loop quantum gravity about some sort of spin or some sort of network? I guess it could be a.
Yeah, spin
Okay, and
network.
this network doesn't really exist in space. A bit
Uh,
like how like
mm,
on the internet, this computer is connected to another computer, and then that computer is connected to another computer via the whatever pathways, maybe telephone wires or what are those things called, fiber optic cables or whatever.
mm,
So that's a network, and then if we were to run a trace on the network,
mm,
what do they? There's a word for it where you ping the network and you get you find out you want to ping I don't know, a website, but you want to
mm,
go find a trace path to the website, and it will tell you which nodes you have to connect to, which IP addresses as you go through the
mm.
system. But you could connect to the first node you ping, then or trace could be in, let's say, Russia or something, yeah. And
Mhm.
then the next node is just down the road from you. But
Oh.
so according to the system, the network of
Mhm.
IP addresses, you are closer to the Russian node than you are to the one down the road from your house.
Wow. That's
So
interesting.
that's what they mean. So when they're talking about this network, it has no relationship to our own space. It has its own logic, which is its own space. And so I don't think it's correct to say that this is, because this idea of granular space-time,
Uh-huh.
that sounds like it's made up of a load of grains, like grains of sand, and one
Mhm.
grain is a grain of time and the other grain is space or something. And so it's discrete at a very small level. But would that be true of this network that I've just described? Well, it could be. But is that something that we're going to see then in physical space? I doubt that, because it sounds like an abstract construction. It's like we cannot see the space that I just described we can see it through a terminal on a computer, but it's still an abstract thing. So they're actually saying, maybe they're just taking that as the initial concept and then they're reifying it and saying, no, there is an actual. But then how would that manifest in space? Because let's say there's a particle on the top of my finger, and then there's another particle in New York sitting on the Empire State Building or something. But according to the network, they're right next to each other. But then how would we ever observe such a thing? We'd zoom in really far into the universe until we get down to the network, and then we'd see those two particles are actually next door to one another. It just doesn't make any sense. You know what I mean?
No, is it possible that one is a wireless system, the other one is a wired system? The wired system has, you know, uh,
Hmm.
communicates through conduction mechanism. It has
Hmm.
the electron conduction. Wireless system is wave,
Oh,
entirely
yeah.
different process.
Yeah. maybe something like that. I mean, obviously, I don't think that would solve the issue that I just brought up there, but I mean, I think it kind of starts going back to a bit like what we were talking about with local and
Yeah.
global. It
Yes.
sounds a bit like that because a local thing might be a wired connection, and a global thing might be
Yeah.
more of a
Wireless.
Wi-Fi kind of thing. This is an interesting thing to ponder, but I
Yeah.
think we'll move on anyway. Connections and implications, unified framework, experimental challenges. Oh yeah, of course. Okay, next slide. Let's have a look at the next one. Gauge theory, gauge invariance. All right, so gauge invariance is a big one. So gauge fields. Yeah, so we looked at that. So when they're talking about local transformations here, like a local gauge as opposed to a global gauge. See, the thing about global gauges is that they're very simple, aren't they?
Mm-hmm.
So if you
Yeah.
have
Actually, like a U1. U1 is a global, right? Isn't it? Global U1.
oh, it probably is, yeah. But could it
And you
be
talked about SU5
also local
last week.
though?
It'll
Could
be
it,
very local, right? SU5 will be very local.
well, couldn't it like it's difficult to remember the all those concepts off the top of your head, and you need to go back and sort of recap, but there's something about
Is it about confinement? More about confinement, SU5?
no, I think it's to do with so this like if I have a field like a spinner field and
Uh-huh.
it's moving around locally, um
Uh-huh.
uh as it's being disturbed by, let's say, the electromagnetic field or something, and it's moving around. It has a spin too, so spin 1/2, sorry. So it's going around twice. And as it's being perturbed, it might be being perturbed by like in a space-time coordinate sort of way. So it could more energy, it's going around faster, experiencing or slower. So when you do all these transformations, then with the Lagrangian, just to find the energy of that system after being perturbed by this other field, you discover that there's an invariance, and this invariance needs to be removed. When you go through the calculations, you find that it is a particular term, so you just minus the same term from it, and that removes the. So it's like having you want it to be the number 5, but we get an extra 3. So how do we get rid of that? We just stick a -3 on the end, and it disappears. So, but then you ask, well, what is the 3? And then you find out, oh, it's just the 3 directions of space, let's say, or the 3 ways that it can be transformed in space. But in actuality, in this gauge invariance of the spinner field, it's actually 6 dimensions, because 3 for the electromagnetic and 3 for the 3 for the electric field and 3 for the Maxwell's equations with the F nu mu whatever 1 times 1/4. And yeah, so those things are real things. It turns out that the gauge transformation is just the electric field. I think I'm saying that right, the gauge transformation. But yeah, the global one then is way simpler. It's just the fact that, oh look, we have if it's like something and it's infinitely distant away, or it just ceases to
Photons,
have.
for example. Photons are automatically, they propagate immediately, right? They don't have any mutual, they can mutually go into each other. So the photons instantaneously become global.
No, I
Global
think
field.
so. So you have
Becomes
like it's like charge. Let's say it depends on what we're talking about. So charge conservation, let's say, on a local sense, because that's what we were talking about with the spinor field, right? That was about charge conjugation, essentially, or conservation. Sorry,
Conservation.
yeah. So we have, I think that's what it is anyway. So then, if you global charge conservation, just reading it here, you take some d divided by dt, and then the integral over the 3 different dimensions times, and that's for all of space. Then your integral for all of space goes to infinity, right?
Mm.
Which means changes the which is what? It is basically 0 or something, or it's infinite. I guess it's infinite. Go. I don't know. I didn't. My notes on this subject are not as clear as I expected.
No. Yeah, the electron field, for
Oh,
example,
sorry. I think it's to do with this idea of current going into some area and out of some area, right?
Mm-hmm.
So you have this box, and the charge, the current density, and the charge and all, and you ask, is it going into or out of the box? But if you're taking all of space, then your box is all of space. So the charge can't go inside or outside of that. It has to be inside it. So, that's a global, that's globally conserved then. Which that's so much simpler than if we're dealing on a smaller scale, because then we have to say, well, what's come into the box, what's gone out of the box. It's a more complicated issue. And then if you have this, if you have some other field affecting it as well, it becomes even more complicated. And then if you're dealing with, like, I don't know, the strong force as well, and it becomes again more complicated. But all of those 3 forces are kind of easy if we're just saying, separately, even if they're just exist, not interacting with any other particles or systems, even if they are, but as long as they don't start interacting with gravity, because then I think that introduces another invariance, and it would be a local invariance, I guess, and that needs to be accounted for. But I'm not entirely sure if they have the right formulation of general relativity yet, and especially there seems to be some. We might get into that another day, but there seems to be some problem with the special case of general relativity and then the general case, and how the 2 link up. So it seems like they're getting. So that's really it. So when we talk about a local, what did we call it? Local transformations of gauges versus global. That doesn't have any. It doesn't have any direct connection, let's say, to when we're talking about a local or hidden variable local causality. I mean, it does have a broader connection, like overall, if you're talking about physics, but if we're getting down into the details, these seem to be 2 very separate kind of things. That's fine. Classical electromagnetism. Yeah, so that's what you're talking about, electromagnetic potential. I can barely talk. Right, modifying classical fields. Yeah, you brought in Yang-Mills theory, which I thought was interesting. You mentioned something that I found. Yeah, describing the strong and weak nuclear forces. Yeah.
Yeah,
go on.
Yeah, one of the things I think the electron field is more localized because you are charged, so the charge confinement, things like that. But the photon field is more global. I think that's so. It's a difference between electron and a photon. I think.
Well, I mean, are you talking about the idea that the electromagnetic field is infinite range?
Yeah.
But yeah, because I was thinking about that. But let's say we have some sort of device that's able to generate electromagnetic field, and even a beam of light or something once it's switched on. So then there's the source element you're talking about, and then there's the propagation element. So you might switch that machine on, and then it begins to radiate, and it has infinite range, so it can propagate infinitely, but it's not going to do that. Yeah, I suppose so. Yeah, if it has infinite range and it has infinite time to fill that infinite range, assuming space is infinite, then that would become a global thing. But I think, like, yeah, I think the global thing that they're talking about here is like, let's say I have a balloon, and the universe is the surface of the balloon, and on that surface are all these little bits of glitter that are kind of moving around somehow, just through static electricity or something. They're just all moving around.
They are charged. They are charges, right?
Yes, yes. And if I draw like a little box, just if I imagine a little box on the surface of the balloon, and I see, 3 positive charges went into this box and 2 negative charges left. So after I tally up all the charges, I say more positive went in, therefore, and more negative left or whatever. So therefore, this area now is more positively charged than it was before this event happened, before the particles moved in and out. But then if I try and do the same with the entire balloon, and I add up all the positive and negative charges at any time, I will always get the same answer because of conservation of charge. Because there's no new bits of glitter being introduced to the surface of the balloon ever. That's not possible under this concept, you know. So assuming that's correct, if we minus the positive charges from the negative charges, we'll expect that it will always be 0, right? Because it should be even. That's another conjecture. So that's the difference between global and local. Just describes as simply as possible, and I hope that.
Another one is like battery. Battery is the one that is
creating that charge. Yeah,
that's local. That's like a box in local.
Right.
Whereas outside that battery, you produce electromagnetic wave in the form of light. So then it can travel infinitely, right? I mean, once you produce, but until it produces, the charge is confined. The electrons are just going around.
Right. There might be other ways of looking at it. Yeah, I'm just talking very narrowly about maybe one equation. So, but I don't know if a gauge field. I don't know if would a gauge field have anything. Would it talk about that, like light propagating from a torch, let's say?
Yeah.
I don't know if it would, but locally you could say there's something going on there with the battery, and once you switch it on, maybe then you would have new fields forming which would interact with bosons, which are electrons and stuff, and then you'd have like all sorts of local gauge things that you might want to. Yeah, you'd have current flowing in and out of different parts, and I'm sure that's something somebody wants to calculate, but I don't care.
Oh yeah,
me personally, I don't need it for anything that I do in life, but obviously it's very important.
Hopefully, artificial intelligence will come to come to your rescue. All this calculation.
Yeah. Well, I suppose you only kind of focus on the things that you're interested in, and then. But the last thing you want to do is like be blinkered to the things that you're not interested in, because there could be a solution there, or you could find out that okay, you're like I'm trying to do all this gauge field work using the 600 cell and the 120 cell, but if I don't understand, if I think that if I just come up with my own idea of what a gauge theory is, it's a dial on a wall that you tap and tells you when you're in the red or something. That would be completely wrong. It would have nothing to do with what it is. And then when they look at my work, they'll go, well, this is just stupid because it doesn't have. But that, to some degree, I don't mind if it is a little bit like, I wouldn't want to just repeat what they're doing, because while it has been successful, it is also, on a lot of ways, it's also been a monumental failure as well in other ways, you know? So
yeah, it's like chasing the tail of a dog or something.
Yeah, so we don't want to just repeat what they're saying. We need to break out of the mold. We need to create new things. and we also need people to like connect their research to ours, and as we're doing with them, we're trying to connect and we're trying to solve the same problems they're solving. Hopefully we're just solving them better and simpler, and that would be the goal. So theory is the basis. So the Yang-Mills theory forms the basis of the standard model. Describe it. Yeah, so that's a huge one, isn't it? So, but we won't get too bogged down into that because that's a total mess. Actually,
you described last time about the Yang-Mills. We had a discussion in your SU5 presentation.
Yeah, that was fun. I enjoyed that. I was like, okay, we're done after about, what was that, an hour of talking about SU5. But there was still, we were only halfway through the
and also the geometric ways, the Yang calculation and the algebraic way of calculating things, how the sets are formed, subsets and everything.
Well, that's it. Yeah, that's exactly what I'm trying to get at with the 600 cell, 120 cell thing. It seems more geometric, whereas so it'd be nice if I could start doing it. It's really amazing what they did and how they understand this SU5 set of matrices so well, and all of the the irreducible representations, and like I'm doing that as well. But the groups I'm working with are a bit more intuitive. They're symmetric groups, so I don't know. They're just easier. But there's big things there as well, and I mean another.
Are there Lie groups? Are there Lie groups or
they are? Yeah. I think they are Lie groups, but that's a kind of another. Again, that's getting very kind of technical. So apparently, so here's the thing: the 600 cell has some sort of transformation group called the Icosians, which were actually, I think, invented by Hamilton as well. He also came up with the quaternions, and basically, it's just a closed group of rotations. There happens to be 120 elements in the group, and it also connects with lots of other groups like SL25, and it connects even with E8, and so it is it's an exceptional Lie group in that sense as well. But it's only half of E8 that it conforms like a coset, and then you have So technically, it should work. Like I don't think physicists would be saying like, "Oh, this is wrong." But then, because of how complicated and, as I mentioned, kind of abstract or obscure the maths in the standard model is, and because of how simple and like bright everything is, what I'm working, it's like, oh, this is blue and this is red, and it's like I'm playing with blocks, and then so they could just say, well, yeah, okay, but how does this connect to this? And I'd be like, I don't know, you figure it out. You're the expert, like. But then they'll be just like, well, I've got better things to do in my time. I've got money to make, and that's just a sad fact of reality. So let's move on.
Next one. Next slide.
Yeah. Okay, so we're kind of back to loop quantum gravity. So this was the point about small scales having discrete structure. See, that to me reminds me of the whole granular thing about space-time. But then my understanding of loop quantum gravity is more like this abstract network. So those two things are kind of conflicting. You mentioned spin networks. So they are talking about those spin networks. These are graphs where edges represent. Yeah, that's funny, isn't it? Edges represent quantum states, and the nodes represent interactions between the states. So it's something very evocative about that, and I like it. It's like from a maths point of view and stuff. There's and it kind of connects with my work a lot, where there's a lot of edges and nodes and stuff. Although, see, the problem is with the interaction side of things is that, so if you have two particles and they're connected by one edge, then you have this particle interacts with this particle. That's your interaction, but it's limited to like two particles then, isn't it? Unless you have three edges meeting, but then it's always going to meet at a point, which would be Oh, wait, so the nodes represent the actions, the interactions. Okay, so that makes sense. Yeah. Having the nodes as the interactions make more sense because you could have like you could have two particles coming in and one particle leaving. So positron, electron, and then a photon. And that's good. But like if you look at maybe, my work or E8, Theory of Everything, Garrett Lisi's work, you would have like you take one particle, I assume you multiply it by the group and it would send you to another particle. So, you have this particle interacts with this particle. Or, yeah, and you do get a third particle out of it, but it's not always what you might expect. But you're not going to get like a fourth one. Like, what if you start with an up quark, you multiply it by a W boson, then you'll get a down quark out of that. But then what about the electron that's created, and what about the neutrino, So you need more branches. So I think that's what's good about this. Maybe it's possible to convert it's possible to convert the nodes of the 120 cell, or it's possible to convert the cells into nodes or vertices in 600 cell just through the dual action. So maybe something like that. I don't know. I'll have to think about it a bit more. I'm just thinking off the top of my head.
The node is actually, so you can think of like Kirchhoff law, the node, so coming out and coming in, follows some kind of a Kirchhoff law, the flow, the actual flow.
Well, that's, because so what was Kirchhoff's law, flows of currents or something, is it, or no?
Yeah, what is coming in should be equal to what is going out.
Oh, okay, really?
You sum it. When you sum all of the thing coming in, and that should be equal to sum of all the things going out. In a simple way.
Yeah, I've heard of that. All right, so it's kind of going back to the point we're making at the box, is it, on the balloon surface? You have the So the charges. So that would be the conservation of charge then. But different areas on the balloon could have different charges.
Yeah.
But what if you went to that area and said, like, well, I'm just going to bombard this area with like a lot of positive charge or something?
Oh yeah.
Does nature's going to react to that by sending out a lot of negative charges or something, or so like?
Yeah. See, the question of system and subsystem. So you have system, you are looking at the whole thing, where subsystem is also a system. So just we are concentrating like a window. In that one, what is happening? In that one, what is happening? So in the window, you are burning in that, in that window. But is it confined to that window, that bombardment? I think that's our question. Like well, if you have laser, maybe laser. They're sending like laser.
It's meant to be confined, like we're just sending the particles in. So we're altering the local charge of that area. Yeah. So I wonder would Kirchhoff's law apply in that sense, because it's not a natural phenomenon.
We like, still withdraw. There's a node that there's a node that something is coming in, and this one they together make a node. In that node, the Kirchhoff law will apply.
Okay. Yeah, I'll have to look into that. Matrix models.
It's like a virtual node, I would say. It will be like virtual.
Yeah. Actual. Chunks are okay. So, yeah, because I think you're probably right. Maybe the spin network creates cells which become quantum space or something. I'd say this is. I haven't really looked into loop quantum gravity that much because I just find it very confusing.
Yeah, I think some of the concepts are useful. That's why I put it, because I think even if you go M3AD, we still have to look at these concepts. Some of them are quite valid, quite useful.
Yeah, there's something really cool about it, and Lee Smolin is a cool guy. He has that I don't know. He's got like some sort of New York kind of vibe going on.
yeah, presence of mind. I mean, what you call a realistic, practical approach to some degree,
Yeah, it's
practical
great. I
sense.
mean, I like it. So, and you know, I think it's being tested, and you know, there's problems with it. I think you mentioned Robert Cavelli, or what's his name? We'll get to his name later, but he works with Corelli, is it? Roberto
Or Ravioli, Rivoli,
Ravioli. He's
Rivoli.
one of these slides. His name is Cavelli, is
Yeah,
it? Cavelli?
we'll go back there. It's there. Rovelli, Rovelli,
Ravelli. Okay, yeah, yeah.
Rovelli,
What was I saying? Jeez, Ravelli. Sorry,
Rovelli. Yeah.
that's my yeah.
All right, it's all right. Yeah,
Okay,
you have a
so
way to check it.
Ravelli, yeah. I'm not I'm not as like blown away by him when I hear him talk. It's just I don't know. I think he's a bit too ideological or something. But he needs to
He's
focus.
not a he's not a this thing for Nobel Prize or something. Was he considered?
Was he?
I
Did he
don't know.
not get it? No.
He has a lot. He has done a lot. I don't know. They will probably in the
Yeah,
future.
he's a big name. I think he's done a lot of good work. He seems to have written a lot of papers that are very high end, and
Yeah,
yeah,
I
he's
looked at some
well
of them.
respected. But I think there's a difference between maybe like a researcher that's good on paper, maybe. But just like when I
No, he
find
has good philosophy. He does go into the philosophy and
no, yeah,
that
no,
philosophy I like.
I believe he has a philosophy. I don't know if I agree with his
Quantum
philosophy.
gravity. Yeah, quantum gravity.
When
Trying
it's
to.
talking about philosophy, like on physics points, yeah, he
Yeah.
might be good on that. Yeah, but no, I think I've watched some of his interviews, and they're
Mm.
not for me. I think they might
Ah,
appeal to a different demographic with a different philosophical outlook. Or just to me, they're not
where is
that.
he from? Where is it? He's
He
not
sounds
Italian, right?
he's
Is he?
Italian, doesn't he? But
Yeah.
I don't know. Is he Italian? Is he? He's not Italian American
Sounds Italian.
because
Yeah, it sounds Italian.
he's a strong accent. So I would
Mm.
assume he's Italian. Boundary maps. Recent research in LQG explore the concept of boundary maps, where quantum states of the bulk geometry. Okay. Right. So this is kind of going back a bit to the holographic principle in a way, or
Yeah, yeah. At CFT.
yeah, which helps to understand relationships between bulk and boundary. Yeah, I mean that sounds like fun, doesn't it? It just sounds like they're
Yeah.
having a lot of fun
Oh yeah.
over there at the Perimeter Institute. Yeah.
Seeing everything together in one picture, I think it's very boring.
Oh yeah.
So that is
It's great. It's good
that
fun.
will be great if we can come up with that.
Yeah. Okay. So, alternative approach. Matrix models offer an alternative approach to describe quantum space-time. Really? Yeah. These models quantifying degrees. Oh, so we're back to degrees of freedom, which of course we discussed probably.
Yeah, it's a very most. I think we should highlight that, or we should keep that in mind about what you said about the degree of freedom constraint. It may solve some problem. I mean, the entanglement. And also, I got a question: if this entangle, then how can you have separateness? So if it is eternally entangled, suppose two particles are eternally entangled, there's a question of their separation. How do you differentiate them? How do you discriminate, or how do you delineate their separate existence? I think that's a question that comes up.
Yeah, yeah. I mean, I suppose you could have like momentum space, and then
Yeah,
what's the space? Just normal space.
position space or space space.
Yeah, just
Position space.
Yeah, position space. Yes, exactly. So maybe you'd have some sort of quantity, like their momentum would be the same, right? Because they're going to have the same momentum, but in opposite directions, presumably. But their position in space would be different. So you can distinguish them by that characteristic alone. But then I mean, they do say that if you have like two photons, or sorry, two electrons, those two particles are indistinguishable from one another, even though I
Then
mean,
you
they
are
could have.
canonical,
And the reason why they're
canonically transformable.
indistinguishable is because, that when they say a particle is spin up or spin down or left or right, it, it, it has all four of those spins at the same time, I think. It's just when you measure it, it gives you a definite answer. So that's interesting. So that's what they mean by they're all the same, because they all have the same spins. It's just a measurement.
But are you measuring in position space or measuring in momentum space? I
No, you're
think
just
that's.
measuring in reality, like where we live.
But what is the reality? Is it reality position? Is it a mixed space reality?
Well, I think things like momentum space are just abstract concepts, like the Hilbert space or something. It's not a real thing. So when we say like you have a position in your where you are, I have a position. So
So we are
presumably,
not in vector space. Are we in vector space or topological space?
so presumably you live in a position space is what I'm trying to get across. But then who
Yeah.
knows? It could be more like a node network. Like we're actually all in pods somewhere, and even though you know what I mean. Like anyway, we don't need to get into it. But
Yeah, yeah. It's more
uh,
abstract. I mean, more interesting,
yeah,
but
it is
later on.
interesting. But
Yeah,
but going back to the point about degrees of freedom, then more less philosophical,
yeah.
more so
That's more concrete,
when we
I
make the
say.
measurement then of like a part of one of these particles that are all the same, they have spins in all the different directions. If we take a measurement of one of them, then um, that reduces the degrees of freedom. It says
Yes.
it pigeonholes the particle into being like spin up or spin down or whatever at that moment. And we did it for another particle, it would do the same for that, but we might get a different answer. But it's interesting that the measurement destroying degrees of freedom is would
Mm.
also be the same for the entanglement. So
Yeah.
and yeah, because so there's that issue. Yeah, it's fun. It's fun to think about it. It'd be good, like kind of thing to
There
meditate
are
on.
orthogonal space, like measurement occurs, in that space versus the entanglement. So they don't interact with each other. Then that will be interesting. So entanglement in a one direction, or in a domain, or what you call a space, then it decreases that entanglement. But the one in the orthogonal to that is a measurement, that reduces. So these two restrictions on the what you call uh, the degree of freedom, right? They are restricting or constraining the degree of freedom. They are the two things are different. The way they affect is different. One of them means one space could be a tangential space. It's affecting. So you are measuring in one space, and entanglement is occurring in another space, orthogonal to that, probably. So then in that case, that probably explains something about a measurement. I think that could explain about a measurement.
Well, yeah, there's this interesting thing that a measurement and an entanglement are supposed to be kind of the same thing in some sense. So just
Ah.
wondering then.
So in a way, measurement causes automatic entanglement, perhaps.
Yeah, because the device is entangled with whatever it's measuring.
Entangle. Yeah.
Yeah, because that's how you get the results back because it's got the same state, I think, as
Entangle.
the
Yeah.
yeah, something like that. And then so but that begs the question then, if you have two particles that are entangled, um, are they like in some sense have they lost and have lost a degree of freedom because of it?
Identity. They lost identity to some degree.
Yeah, some sort of, but or have they gained identity? Have they said like, well, no one's measured us yet, but we are actually now both spin left or both spin right?
So like a test particle, right? One test particle is measuring the other one, right? So they are the test particles entangled with the observed particles. Uh,
Yeah.
so in that sense, they have automatic I mean, entanglement. So when you measure it, you are measuring the entanglement. Actually, you are measuring the, measuring the entangled state is the measurement.
Yeah.
Measurement intrinsically is an entangled state.
Well,
Measurement
wait a second. Maybe
intrinsically is.
the particles, though, are when they're entangled. Well, that's a funny thing, though, right? Because if the two entangled particles are like all other particles, they couldn't be, because that would mean that they spin both left and right and up and down, which would mean that they're identical to each other anyway, aren't they? And then
They should have separate
which would mean
existence.
that they look the same. So they must have an identity that they both share, I guess. But I think maybe what would be better than to speculate would probably be to look into the maths, and hopefully that would, because that's where they got it from. So hopefully that would clear it up. I think that's all we can do. Excuse me. Let's move on. These models use quantifying degrees of freedom of space-time, or provided. Oh yeah, this one, quantized cosmological space-time. Sounds good, doesn't it? Certain solutions. Yeah. Quantized cosmological space-time. I just like the sound of that.
So everything is like grainy. The whole space.
It has a bit of a ring to it, It's like where the fluctuations of these fluctuations of matrices give rise to gravitational phenomena. That sounds good, actually. I'm gonna take a note of that and just look into it, because I haven't really heard of that before, to be quite honest with you. And when are these models came up with? Did they come up with these in the 80s or 90s?
I think it's pretty close. I think it's probably post 2000. I would think even.
Oh, really? That goes to show
many of the graininess. I don't think graininess is pretty recent.
Well, the whole thing about 90s. Granular space-time and all of
that. Much later than Bell's thing.
Well, I mean, granular space-time was talked a lot about in the early 2000s, I remember.
Yeah.
Maybe in the 90s as well. But I don't remember.
Late 90s.
Yeah, I don't remember any of these other models. So I'll look into that. Quantized. Excuse me.
Yeah.
I'm gonna have to go and get something to eat at some point, but this has been interesting anyway. Because otherwise, okay. So bulk boundary correspondence. So that's okay. That's kind of, you talked about that already. Emergent properties both suggest that space-time. Right. Okay. So what's the next one, Rajan? What's the next slide? Those are all. They're great. Oh, thank you. Great. Okay. Those are all. They're great concepts. What? There's a few more. Right. Well, there's all of these, but I think what I'll do is I'll rewatch this later and I'll go through them myself.
Okay.
You've upcoming YouTube live broadcasts. Question is what is this question here?
So I have put two questions, and then we can discuss later. I don't have a complete answer to that. That's why I put that question.
Right.
But is non-locality electromagnetic wave that we are in a way saying that, like the globalization, that as soon as a photon or electromagnetic wave is formed, immediately they become available everywhere. Like you shine a torchlight, light becomes immediately, instantaneously goes to the other side of the room, kind of.
But that doesn't happen though, because we know that light propagates at the speed of light. Yeah.
Yeah, that's the question. Is it instantaneous or speed of light?
But we know.
Is there a path? Is there a path? I mean, even then it can become non-local, right? Even if the speed of light, it can become non-local, right?
And non-local, but non-local doesn't mean, when we're talking about non-local, we're talking about particles entangled sharing similar states or opposite states.
Yeah.
So
Yeah.
so if I have a torch and I'm shining it into the darkness or whatever, into the
Yeah.
night, there's no entanglement there. Nothing has been entangled. It's
It's a
just
propagation. Just a
yeah.
propagation.
So that's it. So I mean, maybe you can entangle beams of light using silvered mirrors, is it, and reflective surfaces and
Yeah.
stuff like that, and polarization filters. So you can do some very interesting experiments. Actually, I seem to be plugging this guy's show a lot. Not that it's going to be any benefit to him, but Kurt Shane Mungel's theory of
Yeah, he had another person from
yeah.
Harvard University recently. He
Did you
talks
watch
about
that?
stochastic process.
Yeah,
The
that was
one
interesting, wasn't it? Is that
that
the
was
guy?
that.
That was the guy who said Hilbert spaces don't exist or something.
Yeah.
I was talking about him last week. Yeah, he's good.
Uh,
Although I think
I forgot his name. What is his name?
yeah, I
He's
forgot
in
his name as well. Is it?
Harvard. He's in Harvard.
He's from
He's in
Harvard.
Harvard.
Yeah, I think so. Yeah. Is it like Bernard or something, or Brendan or something like that?
Bernardus.
Right.
I think it's
Yeah,
Bernardus.
nice guy.
Bernades. I think Bernardus.
Right. Yeah, and that's his first name though, isn't it?
No,
Anyway.
last name. I think Bernardus.
Oh, okay. Well, we'll look that up, but people can check him out anyway. But I couldn't remember his name either last week when I was talking about him. That's funny. And then, I believe it was last week. So then this new guy called, and I do remember this guy's name.
Kurt J. Mangal is interviewing him. He's a
Professor.
what is that? He's actually a YouTube poster. What is it? Podcaster. I think
Yes,
Kurt J.
Mangal.
Mangal is a podcaster.
Yeah, I think he has some science background as well, physics background.
Yes, he knows all those. He's
knows,
doing work on some content.
Yeah, he's quite good. So he doesn't dumb it down generally, although sometimes his questions can be a little bit like, for instance, in that interview, he never asked. He had the guy there on the hook who said he could explain the apparent paradox of the double slit experiment, and yet he never asked him any questions of like how it solves it, stuff like that, where kind of obvious questions. Which, see, the problem with questions like that is they are a little confrontational. It's like, oh, well, you say you can prove this, well, go ahead and do it then. And if the person isn't able to do it, you've just like crushed them in front of an audience of millions of people, which they might.
But he did mention that another session we will have.
Wait a second, but like, if you're
mathematics.
going to make some claim like that, in front of millions of people, you should expect someone to say, like, okay, we'll do it then. I can explain it. But instead, he sits there for 2 hours and doesn't even. He says, "Oh yeah, I can explain this," but then he doesn't do it, which I find a bit annoying. It's like this. This whole thing where someone tells you something about like, oh, anti-de Sitter space, and then there's this space and time then before you hear about it again. You're like, I still don't know what that is, or this kind of obfuscation or like drip feeding of information, and then 10 years down the road, you find out, oh, it was all just smoke and mirrors anyway, just to get more funding.
Farcical.
Yeah, exactly. It's like, oh, well, you believed me for 10 years and I got like millions of funding out of this, so I don't care. See you later.
I got you there.
Suckers.
Gotcha.
Yeah. So that's what I'm worried about with these people. They're crafty. Although no, I think he's a good point, but it's probably no better than half of the stuff we're coming up with on a flipping weekly basis. But anyway, let's move on. Is Locality
it's a hidden variable gravity? So he's a hidden variable, actually, gravity. The local sun.
I think we looked into that. The hidden variable is loss of degrees of freedom. So, it could be kind of more.
Oh, the larger thing is that is the global thing inducing the local thing.
Gravity is increased degrees of freedom, isn't it? Wouldn't you say?
Yeah. So the global thing is inducing the local thing, or the local thing is, globalizing or propagating into the globe. The local thing is globalizing or propagating into the global thing.
There
That's
is
the whole question.
thing. There's local gauge transformations, and then there's global gauge transformations, which aren't really gauges, but they're global transformations. I don't think they're gauges. But in this case, it's local, okay, versus non-local,
Oh yeah.
not global. So that's what I'm saying. These are two
Yeah,
different
there's a difference. Yeah.
things. Yeah.
Because suppose you have strong confinement, right? The strong nuclear field is confined. That's very local. Very local. But when you become weak, local, it become non-local, right?
Like
When
weak.
it's a radioactive, when it's a radioactivity, it become non-local in some sense,
I know. I
right?
don't think
But
that's
it's
not what.
not global. It's not
Yeah.
global per
I
se.
don't
It
think
may
we can
not be
use.
global.
I don't think we can use the terms local and non-local in. They're not meant to be like used in the sense like local could be like hundreds of kilometers, you know,
Hmm.
a non-local.
Relative. So it's relative.
Well, actually, it doesn't. See, local and non-local. It really depends whether you fall on the.
Subsystem or system or subsystem.
Presumably, we now understand what Einstein means by hidden variables, and that he's talking about in a local thing, and that as the particles move away, they become more disentangled. Okay, excuse me. So, and there is no faster than light communication. It's happening at the speed of light. So, but that is the dispute. It either is happening instantaneously and it spreads across the universe, or there's these hidden variables. So when it's talking about, so that kind of muddies the water. But if we're just talking about, if we talk in the language that entanglement is encased in, which is Bell's theorem rather than Einstein, because we don't discuss hidden variables that much. So that we couch it in that language, and that language, I believe, is local and non-local, right?
Mm-hmm.
Or I might be tripping over myself here in my thought process, but what I mean is that a non-local event would be, yeah, I could be making a hames of this, sorry, but a non-local event would be this particle is measured a spin up, therefore a particle on the other side of the universe instantly becomes spin down. And the fact that it becomes spin down means that it was in a superposition before that. Okay, so that's a non-local event because there's nothing connecting those two particles. But if you were to bring those two particles close together and that transmission of information is still instantaneous, then that's still non-local, even though they're closer together. And then I think local would be the opposite. It's like what we imagine the universe to be like on a normal day-to-day basis, and the one that
Is it
Einstein.
same as continuum? Is it same as continuum versus non-continuum?
Discrete.
Yeah,
Continuum.
discrete. Continuum versus discrete.
No, it's very different to that, I think. I wouldn't get. Those are two
They
different
are
things.
all different.
Yeah, I would keep them separated. Okay. Okay. So is hidden variable gravity matter? Well, first off, what does gravity matter? You mean the particles matter?
Yeah,
Like
but they are discrete particles.
gravitons.
Discrete particles. Yeah, gravitons, for example.
Oh yeah. So again, I think gravity would introduce more degrees of freedom, which so, and a hidden variable is degrees of freedom that are being lost. So I don't think so. So I think there's a definite contradiction between those two statements. But still, good fun.
Oh, okay.
But I mean, there's a huge
Okay.
there's lots to talk about there, and I
Yeah.
will look through your references, which is great.
Yeah.
And then we'll won't see each other next week. So I'll try and send
Oh,
out.
you said nothing next week, so it will be Next week will be 30th.
Thanks.
So it will be more
Thanksgiving.
like the 7th, more like the 7th, I think, of December, right? We'll be meeting next.
Right. Yeah, I think something like that. So, okay. See you then.
You let us know. Okay, have a nice time with your family. Thanks.